Oh, before you start it. Yeah, that's good. I was like oddly nervous right before talking. You can tell if I'm like, okay, what do I say again? It's really nervous. And I presented these slides like 5 times. The like intro to Python. This has been refined at this point. It's pretty straightforward. It's been a while since I think the last time I presented. Hello, everyone. Hi. Well, welcome to the inaugural PyHC 2022 Summer School. Thank you so much to everyone who's been able to make the trip over here in person from wherever you came from. We greatly appreciate your presence and hope that you enjoy this summer school. And to those who are attending remotely, thank you for your attendance as well. Unmute myself. Or not. Don't. Okay. Cool. Well, I'll start. So I introduced myself earlier, but in case you missed it, I'm Julie Barnum. I'm the principal investigator for the Python and Heliophysics community, or PyHC, a NASA grant that runs everything that you see today. And after me, Arnaud will give a short intro on ESA and some things about here, and then Sandy will do another HelioCloud reminder for you all. So before we get into the summer school specifics, I just wanted to give a bit of a background on what PyHC is. I saw a lot of new names here, so maybe some of you don't know very well who we are yet. So the motivation behind the PyHC community was back in 2018 was when we started. So before then, there were a bunch of different Python development projects going on in the heliophysics and space weather communities, a bunch of overlapping needs between various groups, varying standards of how software packages were being put together and developed, a general lack of organized information about existing code within this community, and a potential need for generic libraries across the projects and communication in general. So that was really what spawned the efforts behind PyHC, was wanting to help fix all of these problems. So we came up with a mission statement to do that, which is, as you see, facilitate scientific discovery by promoting the use and development of sustainable open source Python software across the solar and space physics community, improving communication and collaboration between disciplines, developers and users, and establishing and maintaining development standards and fostering interoperability and reproducibility. So to date, we've successfully created a centralized location for information on all things Python and heliophysics. We have a bunch of different projects we've brought together under the PyHC umbrella at the link that you see here. We have just under 70 projects that we've put in there so far, and we have several 4 projects, which you'll hear from at this summer school: PlasmaPy, SunPy, SpacePy, PySat, and then PySpeedas, not HelioPy. Sorry about that. We also have several other widely used projects that you'll hear from, Komodo, Happy, and so forth. And we cover a wide range of domains when it comes to the projects that we've identified so far. We have solar, heliospheric, geospace physics, the magnetosphere, and the ionosphere, thermosphere, mesosphere. And as far as our software capability goes, there's a lot of different things our projects can do. We have projects that are focused on modeling, machine learning, plotting, wrappers for other libraries, and so forth. And in order to best direct all these projects and make sure that they're all up to the standards that we hope for, we created a set of standards, actually, that all of our projects are required to follow. These were based on the AstroPy standards that are posted on AstroPy's website, and you'll hear from AstroPy today, actually. And were selected by consensus of our community at our fall 2018 meeting. And you can see that there's 15 different standards that we've asked our projects to follow. So yeah. As far as activities, so we hold telecons on a regular bi-weekly basis. These include various things like new project intros, updates, discussions amongst the community, outside invited speakers, and so forth. Everyone here is, of course, welcome to attend whenever they would like. We usually have a session at AGU, so if you ever want to check out our poster session, I think this next year we applied for a hybrid, so hopefully we can see some people in person. Twice yearly, we meet in person for our annual meetings, at least theoretically. That's changed with the pandemic just a little bit. And those are open to seasoned open source Heliophysics Python developers and newcomers alike. And then, of course, we have a summer school that we're holding for the very first time here today. And this will introduce our PyHC software ecosystem and help create an understanding of how to use these packages in your research workflow, how these packages could benefit your research workflow, and how to then use them locally, and have a little bit on Python best practices at the end of this meeting. So if you'd like to connect further with us apart from just here at the summer school, there's a bunch of different links in here. We're on a lot of different social medias. If you're on Twitter, we just made one, so come follow us. And I'll make sure to post these slides in the general Slack. So for some summer school specifics now. So as you all probably know, there's the link to our summer school webpage. It has a bunch of different localized information on it, so make sure to check that if you're ever unsure of something. Or you can always go look in the general chat in Slack. I pinned a bunch of different links that were pretty important for everyone. We're going to be using the Zoom webinar platform, so if those who are on virtually, you've already figured that out. We sent info about that out in previous emails. If one of these days, if you're attending in person, you end up staying at your hotel, just check the general Slack channel for how to log on. This is also being streamed to the PyHC YouTube account for those who didn't register. So if you want to share this with any of your friends back home, feel free. And then we're going to be using the Slack space as far as Q&A and all that goes. So as available for all registered attendees to use to chat, coordinate meetups, and so forth. So I'm sure you've already all logged on to that by now. As far as the agenda goes, like you saw today, we came a bit early so you could all get registered and signed in. The rest of the days, the buses will come to get you at 12:30, probably at the same spot as happened today, I'm guessing. Yes, so we'll make sure to update that on the website where the bus location moved from. We'll have lunch at 1:30 every day, and then the summer school will begin at 2:30 every day. So as far as the general agenda goes for projects, today is going to be AstroPy for Heliophysics and SunPy. We'll hear from PlasmaPy and SpacePy tomorrow, as well as having a buffet dinner provided by ESAC. Many thanks to them for that. And everyone on site is invited. That will be free to you. Day 3, we'll hear from SolarMock and Happy with a touch of Virus as well. And we'll be ending early a bit that day, so you'll have more free time at night in Madrid. Day 4 will be PySat and PySpeedas. And then day 5 is for Komodo, some other PyHC projects to present, and then a Python learning session wrap up. So just some etiquette things to think about. All attendees are expected to follow our PyHC code of conduct at all times. Basically, you can summarize it by be a good fellow human being. So if there's any violations of that, it can result in possible dismissal. So please make sure that you're following that. If you have any questions for presenters, issues with HelioCloud, and so forth, if you're virtual, we have several different channels for each project in Slack. If you have a science or presentation-specific question, put it in there. For example, in the SunPy presentation, if you have a question for them, for the presenter about their science, about something they just presented on, see the SunPy channel. And if you have any tech issues, put those in the tech issues channel, please. If you're here in person, there's a bunch of cards in front of you. We did that to kind of help organize our workflow a bit. If you run into any tech issues, make sure to raise the red card. The yellows, if you would like the presenter to slow down, and the green is if you have a question. And we'll make sure to bring a mic over to you so you can ask the presenter. You can also just post them in the Slack if you prefer. So if you have any general summer school questions, though, put that in the general chat, or you're always free to email the PyHC confidential email. On to you, Arno.
So thanks everybody. So welcome to ESA and welcome to ESAC. I'm not gonna spend a lot of time. Just wanted to say that we are very proud to welcome this first summer school here. And ESAC is basically the center for planning scientific operations of many of the ESA spacecraft that you can see here. We also are the Science Archive Center, the ESAC Science Data Center for all these missions that you see, and also doing data science, so science operations, archiving, and data science. So you can see in the bottom left the Heliophysics science archives that are connected to these different Python packages, and you're welcome, of course, tomorrow for the buffet dinner, and we'll try to welcome as best as we can during all this week. So thank you very much.
Thank you. So hopefully this is recap, but we are using the HelioCloud platform provided by NASA Goddard Space Flight Center. I'm Sandy Antunes from Applied Physics Laboratory, and Jeff Bradford from NASA Goddard will be providing tech support. Long and short, if you haven't logged into HelioCloud and started things up, this is a good time to do so. If you run into any problems using it in your in-room, then the red card, football style, is something that you raise, and myself or Jeff or Julie or Sean will come over to try to figure out what the issue is. I'm going to just briefly go through the steps that are needed for getting going, but you can see it's login, start a server, go into the directory, which is already populated for you, do an optional git menu pull to refresh the contents. Basically, there'll be a menu when you're in the summer school directory that says git. You can go to git pull force and it will refresh the copy. If you don't know what I'm talking about, don't worry about it. You probably can just work with the default set that's there, or raise a red card. And then each notebook will be told to you by the instructor. This is the look and feel of the HelioCloud interface. So on the left side, there is the file browser for accessing any given tutorial that's being taught. And on the right side is the actual notebook composed of cells which contain text and code and are editable during the course of this. So log in, pyhcschool.heliocloud.org. Use your username and password. If you haven't signed up yet, I'd be seriously surprised, but this is your chance to do so. Start a server. You will therefore have your own virtual machine running. Anything you do on that will not affect anyone else. So you can have fun playing around with it. If it crashes, we can just start another one. So it's a very low risk environment. You have the choice in the file menu of opening existing notebooks, or you can start a notebook to have a Scratch Python notebook that you can be doing coding in as well. AstroPy has some great tutorials. I don't know if they're going to cover within their program, but they have some great tutorials on using notebooks, a notebook about notebook. It essentially lets you combine markup or text with actual code. And then when you have a cell of code, you can run it block by block to execute. So breaking it down into cells, some cells have readable text and the others are code blocks. When you click on the We'll play triangle up at the top. It runs the given cell that you are on and executes it. If you're in a hurry, just spam that button 20 times and you can go through the entire notebook in less than 20 seconds, but we're going to be lingering on them to get to the actual content. Notebooks are therefore self-described. So that's the recap of the general format. And again, if you are online, use the Slack tech questions and we will respond to questions right away. And if you are in the room, you can raise a red card if you have a tech question, we will help you.
Okay, thanks everyone. I think we can go ahead and move on to the AstroPy demo and start things off. Presenting today for AstroPy is Brett Morris.
All right. Hello, everyone. Welcome to Madrid. Good to see you all. My name is Brett Morris. I'm currently a postdoc at the University of Bern in Switzerland. And I am a contributor to AstroPy, and I'm excited to share with you today some of the tools that we've developed and continue to develop in the AstroPy ecosystem that might be useful to you, either because they're fundamental down deep within SunPy and we use them via SunPy, or because you might need to use them in your applications as well. Before I get started, I want to say that I'm really excited to be here with you folks because I study stars and planets. The planets might be a little far out, but the stars are kind of familiar to you folks. And my PhD advisor always told me that when we study stars in distant stars, we are kind of pretending to be heliophysicists, where we're doing very, very low resolution versions of what you folks do. And if we want to understand how something really works, we go and reread your literature. So thank you for providing all of the understanding that our field pretends to imagine we understand, just barely. So today I'm going to walk you through some tutorials on AstroPy. And I'm going to start with just this brief introduction. If you are in your HelioCloud summer school repository, there is a subdirectory called AstroPy tutorial. If you click on that, that will bring you to a series of tutorials that we've developed for AstroPy workshops that have been taught mainly at American Astronomical Society meetings. Again and again. And so we've really run these notebooks a lot of times collectively. So I hope they will work for you today as well. The format of this talk is going to be alternating between a few PDFs of presentations that only have a few slides here or there, and then switching to the Jupyter notebooks where we can execute code so that we can actually learn how it works together. I'm starting in the presentation I'm showing you is in the intro and code of conduct directory. If you click intro.pdf, it will take you to the PDF that I have open now. All of this is available in the summer school repo and also at this link at AstroPy/AstroPy-workshop. And Eric is not presenting today, so I'm going to skip over that. AstroPy also has a code of conduct, but again, I think Julie summarized it nicely. If you're a good person to the people around you, you're doing a good job. Please keep doing that. Typically, when we teach these workshops, we do it by teaching you an intro to Python first, which we're largely going to skip over for this workshop. We then do overview of some of the submodules within AstroPy, and we're going to pick a few of those. We're going to skip some of the extra stuff that have to do with domain-specific astronomical work. And the format of the contents of this talk will be alternating between slides that explain to you some of the concepts that underlie the code that we're going to present, and then actually using the code. During this workshop, I encourage you to ask questions. You can ask questions at any time, and I really appreciate the questions because they help me figure out where your level of understanding is. So I welcome that. You have cards in front of you. If you hold up a red card, people will slow down or try to come and help you. In particular, there are a few folks in the room who are very proficient at AstroPy in particular, who have already graciously volunteered to help if anything goes wrong. So if there are any problems, raise your red card and someone will come over to help. Also, all of these materials are publicly available, so you can use them at any time in the future. And I'm going to go through some of them rather quickly and skip over portions of some of the notebooks because they don't all require that you understand them at a very deep level in order to get to SunPy and to the other packages that we're going to talk about. So if at any point something interesting gets scrolled by, you're welcome to go back and experiment with it later. So what is AstroPy? AstroPy can be thought of as two overlapping organizations. One is the core package itself, which is on GitHub as AstroPy/AstroPy, which is an open source, open development, community-driven library for astronomy in Python. The goal is really to catch all of the things that users would have to develop for themselves in order to do astronomical science in Python, and not to cover the use case of every single astronomer, but to cover the majority of the tools that every astronomer needs. There are more specialized packages that specialize in subdomains of astronomy. And then there's the broader AstroPy project, which is the effort to not only develop that core package, but to maintain an ecosystem of packages that rely on the core package that support all of the various specific use cases that people come across in astronomy. Within AstroPy core, there are several submodules, and we're going to talk about a few of them today. They include units, which represent unitful quantities. If you are a PhD student, this will save you so much time on problem sets, and I'm so excited to share it with you. For coordinates, we explain coordinate transformations. For times, we can represent times very accurately across very long durations of time, which is relevant in astronomical contexts. There's also a tabular data format in table. And of course, we deal with FITS files quite a bit. So there's a module for FITS files. There's two distinctions about AstroPy that we like to make. One is that open source refers to the software which is available and licensed in a way that somebody can see it and use it and modify it. And then there's open development, which means the development of the software is actually done in the open. You can have open source code that is not developed with open practices, but we strive to do both by developing in the open, where there are roadmaps that you can read that tell you the plans of the collaboration. There are issues that track the known problems with the software, and you can contribute software publicly and receive feedback on those contributions in the open. And in practice, that's on GitHub. There's also a concept that I'm not going to belabor too much, which is the affiliated packages, which is to say that there are many packages that rely on AstroPy that are not developed or maintained by core AstroPy contributors. And this ecosystem of tools that rely on AstroPy contain a special label for certain packages called affiliated packages, which use AstroPy in abundance and abide by the AstroPy style guidelines and documentation guidelines and open development practices. And so there are a number of affiliated packages that you can access online. at this address. And before I dive into AstroPy specific things, I am going to open that notebook first to explain how you use a notebook. So in the AstroPy tutorial subdirectory, if you open the Python intro directory and then click the 00 using the Jupyter notebook file, you will open this notebook. If you're unfamiliar with using Jupyter notebooks, this will be the briefest introduction you can get to it. So a Jupyter notebook is a way of writing both code and documentation one after the other in cells. And so the cell is the main unit of content in a Jupyter notebook. You don't have to launch this notebook, so we can skip the starting up. But suppose you have some Python code and it sits in a cell that looks like this. I'm going to make my screen a little bit bigger so you can read it in the back. I'm just going to close that for now. So all of the components that you see in this notebook, which looks like a website, are editable. So if you double click on this text, you'll see that the text itself is written in Markdown, and you can get all of the rich text formatting that you might want by making things bold or italicized or look like code using Markdown. Then there are two types of cells, which you can see are denoted over here. So this is a Markdown cell. But if I select the one beneath it, that is a code cell. Now it says a code cell because Jupyter supports Julia, Python, and R. And there are plugins for things like Fortran, if you really want that kind of thing. By default, we are using Python 3 in this tutorial. And so you can execute your Python 3 code by pressing Shift Return on that cell. The output from running that code appears right beneath it. And so you can see that we set A equal to 1, and then we printed A and got a 1. There are special commands unique to the Jupyter environment called magic functions. And one that we like to use a lot would be Matplotlib's magic functions. One is Matplotlib notebook. You might also use Matplotlib inline to make inline plots. And then if I execute the cell beneath, mine didn't work. That's right. Thank you for that. So if I just change that to Matplotlib inline, that will work correctly and generate a plot. We could edit this. If you were running this in Jupyter Notebook instead of Jupyter Lab, it would have done what I expected it to do. And of course, there are great ways of formatting text. You can also format LaTeX in a Jupyter Notebook. And so this is a really convenient way to write your scientific workflow out. So if you don't already use notebooks in your work, I would encourage you to consider them because they allow you to write not only the documentation in either rich text format or LaTeX format, all around the code that you run and the output, which might be figures. Some important notes. This is an active shell, and every time you execute a cell, it's going to take the output of that cell and remember it the next time you execute it. So if I print A and A is equal to 1, it will print 1. But if I change A, it will remember that I changed it. And then if I ran this notebook a second time, it would reset A every time. And so what I want you to remember is that it's possible during your workflow to execute things out of order in such a way that it doesn't know what certain variables are. Or it has certain variables set to old values, which can lead to non-intuitive results because it's not a script. It's not starting at the beginning and running to the end. It's running each cell that you ask it to run. So try to be mindful that you run through each cell and actually execute each one before you move on to the next. And then let's say you really filled your notebook with output and you were done. You can always go to Edit and clear all outputs to get rid of all of the outputs of every cell. That would be the quickest way to make your notebook look like you never used it. Hopefully we're all on the same page, and I will take the leap and jump into a description of AstroPy, which is going to start with units, which maybe sounds too fundamental to be interesting, but I promise you it is worth your while. So ordinarily, in your code, there might be two ways that you handle unitful quantities that we have all done at various points during our work. For example, if you're making a variable called speed, and that speed is 100 kilometers per second, you might create the variable without a unit attached to it in any way, except with a comment that says what the unit is. Or you can make a variable name that specifies the unit system that you generated that unit with, and without a comment. All of that is fine if you're very, very consistent, and if you never share your code. But if you share your code, or you're sometimes inconsistent, this doesn't scale very well. Another thing is that if you saved one variable in one unit format, let's say you used CGS and your friend used MKS, then you would have to learn to speak to each other about when the units conflict with one another. We tried to solve some of those problems in AstroPy using the units module. The point of the units module is to describe all, I'm going to say all, which usually I don't like to say, but try to describe all physical units that a user might come across. Attached to those units values, which we call quantities. A quantity is both a value and the unit associated with the value. And then there are three other concepts, including physical types, constants, and equivalencies that will make more sense when I explain them in a little bit. So unit objects themselves represent a unit, like the meter. And they include the base units like meters, but also you can put SI prefixes onto them like kilometers, and you access them from AstroPy by usually writing this line at the top of a lot of your code. You import astropy.units as U, this is our convention, and then you get access to all of the various types of units that you might come across in physical work, in the physics field, like meters, kilometers, and aliases for those units. A quantity is a value multiplied by its unit. And if you're used to dimensional analysis, you know that we normally think of units as like a multiplicative thing. And so the way that we assign the unit to a value is we multiply that unit by an array or a list or a value. We represent that in code with hopefully an intuitive interface where you would multiply 15 by meters in order to get 15 meters. You could also multiply a list or a NumPy array by units, and it will essentially just wrap that metadata on top of whatever object you've given it to. And then you can convert between units quite naturally. Once you have a quantity, you can take that quantity and type .2 and then reference the unit you want to convert to, and it will give you the quantity in those units. Another thing that I'm going to gloss over a little bit, but then come back to in the code portion of this tutorial are physical types. Each unit has associated with it the idea that it is a length or a time or a dimension of something. And it allows AstroPy to know when it can convert from one system of units to another system of units. Another is constants. Since graduate school, I've forgotten all constants, and that doesn't matter because you can import them all. So from astropy.constants, you would import the gravitational constant big G or the speed of light C, And then you can do basic arithmetic with those unit full quantities without ever remembering to any number of decimal places, any physical constant ever again. And lastly, there are equivalencies. So let's say you're an astronomer who deals with, or a heliophysicist who deals with a line that you've memorized in units of angstroms. And you're trying to talk to a radio domain user. And they're like, okay, well, how many terahertz is that? I would say, I don't know. Or I would say, give me a second, and I would type out this line. What we're doing here is we're saying I can specify length in units of angstroms, which specifies some line in a spectrum. And I can convert it to terahertz, even though terahertz is not strictly compatible with units of angstroms, by using this concept of equivalencies and saying that this is a spectral equivalency. I want you to convert the unit angstrom into terahertz, understanding that I mean via the speed of light. And it will do that calculation for you without you specifying the speed of light. So if you were to execute that first line of code, it would fail because length and frequency are not compatible. But if you specify that we have a spectral equivalency, then everything's okay. So let's see how this works. So I'm going to jump into the notebook representing units, which in the AstroPy tutorial is under units and quantities and AstroPy units. Let's begin. And there's a bunch of links in here that you can click through if at any point you would like more documentation. So I promised you the line that we start with at the beginning of our code, our first substantial line of Python is going to be import astropy.units as u. That gives us access to the AstroPy units module. We can represent a unit by calling u dot and the name of the unit. It understands u dot m to be meters. And if I execute the cell, it's going to give us as output a nicely latexed m. How fancy is that? We have the technology to make an M. There's better things incorporated into the AstroPy units module. Like, for example, there's documentation, which tells you that the meter is in fact the base unit of length. We also have astronomical units like parsecs, which you probably don't care about. Each unit has what's called a physical type. So it understands that a meter is a length and a second is a time. There are also aliases associated with each unit. So u.m could be equivalent to u.meter. U.meter returns the meter as well. There are aliases for arcsecond, which could be arcsec. And look, it even renders an arcsecond symbol. How great is that? Now, let's say you were cruel and you wanted inches. Well, you would receive an error. And it's not just me telling you that you're wrong. It's the entire astronomical community telling you that you're wrong. You should not ever do anything in those units. However, if you insist, we added one extra layer of friction, which is you can go to u.imperial.inch, and that understands what you mean, which maybe is a bit facetious, but that's how we feel about it. Now, we have not specified every possible composite unit, but you can. So if you want kilometers per second, you just divide kilometers by seconds, and you get km per s. If you want miles per hour, go home. But if you have to, this is how you do miles per hour. There are really non-intuitive units that sometimes an astronomer might use, but this one is pretty contrived. But let's say you wanted electron volts megaparsecs per gigayear. This is how you would specify that unit. The point is, AstroPy doesn't care how complex your units are. It will do the math for you on the back end. Cubic centimeters can be represented by cubing centimeters. And here's some more units. Now let's talk about quantities. I told you a quantity is when you associate a particular value with a unit. And so we can multiply 3.7 times astronomical units to get 3.7 AU. You could do a similar thing. You could construct a quantity object by calling the constructor, which would be u dot quantity with a capital Q, and then put in the value and its unit. And that returns the same thing. Fortunately, many aspects of the unit module have already been implemented as layers on top of NumPy as well. So if you have a NumPy array that could be millions of items long, you can multiply that array by the units that are associated with the array, and it will store this quantity as an AstroPy quantity, where really it's just a thin extra layer of metadata that specifies the units on top. Quantities have useful attributes. So for example, let's say we've specified a quantity, which is 5 megaparsecs. I know I'm speaking astronomer and I apologize for that. If you do q dot value, it will give you just the value, just the number, not the unit. And if you do q dot unit, it will give you the unit, but not its value. We can do the same on arrays. In this case, x dot value will give you a NumPy array. And x dot unit gives you just the singular unit. Here's where your colleagues will become jealous of your unit propagating skills. If you have arithmetic, you can do the arithmetic and it will understand how to apply units correctly. For example, if I take 3.1 kilometers and I multiply it by 2, I get back the value times 2 and the unit preserved as it was. I can divide by 2, I can even square it, and it will square the unit as well, because it understands that that operation applies to the unit. You can also combine quantities. So let's say we have one quantity, which is meters per second, which is the kind of unit I would write. And then we have something that an astronomer might like better, which would be in CGS, which is centimeters per second per gram. Sorry, yeah. Who would do that? I wouldn't do that. But it doesn't matter because I can multiply these two together. By default, AstroPy will not simplify your units because it wants to preserve all of the information that went into constructing your quantity. But if the units cancel naturally, it will cancel them. So here, if we divide Q1 by Q2, which both have seconds in the denominator, it gets rid of the seconds for us. If I square Q1, it squares both the units. If I multiply a quantity that has an array, it does element-wise operations on that array, just like NumPy does. Sometimes you have to be a bit careful to remember your parentheses because the order of operations matters in your code still. So if you want to take 3 meters and add to it 5 meters, this is how you would do that. You would get 8 meters, which seems trivial, but you could do this with units where it's not trivial. And by default, it will essentially reconcile the difference between the two units and give you a quantity with one of the two units associated with it. However, there are fail-safes built into here. So if you try to add to 3 kilometers, 5 kilometers per second, you get a long error. And that's meant to scare you, but if you scroll to the bottom, it says, I can only apply the add function to quantities with compatible dimensions, meaning you screwed up. So if I change this to kilometers per second, then it will do the addition. There are several space missions in the astronomy domain that could have been saved if only they used AstroPy units. Now, converting between units is very straightforward. Let's say we've specified 2.5 years. We can convert that to seconds by calling the quantity .2, and then in parentheses, the name of the unit that we want to convert to. How many steradians are in a degree? Doesn't matter. AstroPy units does it. So let's convert square degrees to steradians. That's an ugly number. I don't intend to memorize it, and now you don't have to. You can convert those imperial units to more sensible ones if you choose. And when you do operations that multiply together units that are compatible, it won't resolve them into a more sensible, reduced version of the unit unless you ask it to. So if we wanted this ugly looking unit, which is centimeters and meters, to be converted to meters squared per kilogram squared per second squared, we can specify that as the output unit that we want. And then it will reconcile all of that for us. So it will do the multiplication in its native units, and then it will convert into the units you requested. If you ask it to convert a unit without a value, so a unit but not a quantity, then it gives you the conversion factor between the two. So here's how many kilograms are in a solar mass. If you give it a quantity and you ask it to convert, it gives you back quantity. So there's a bit of self-consistency there. Now let's say you prescribed some atrocious unit like centimeter parsecs per gram per year squared, and you wanted it to reduce that to something better, but you didn't want to sit down and do the unit cancellation to figure out what dimensions it should end up with. You could call q.decompose, and it will give you back the MKS equivalent of the resolved units. So this is the cheating that you get to do with AstroPy units. There are other bases you could use. So instead of MKS by default, you could give it CGS, and it would do the same conversion. You can always check what is in CGS for each of the various aspects of the base that matter to you, and SI units looks like this. As I mentioned a moment ago, if you have compatible units, they don't cancel out unless they're identical. But if you call decompose, then it will. When it cancels them out, it returns to you a dimensionless quantity. A dimensionless quantity is a quantity that has no metadata for the unit associated with it. You can always check that the unit of this dimensionless quantity is dimensionless. Now, I know I've failed at this test several times. The trigonometric functions don't usually think in units of degrees. And this is the bane of my existence because I think in units of degrees. So if I were to call np.sine of 30 degrees, I would get back a number, and then my code would fail later on because I misunderstood my own input to the function. Of course, I could have given it the equivalent of 30 degrees in radians if I remembered what that was, but you don't have to remember that anymore because you can call np.sine on 30 degrees by specifying units of degrees, and it will give you back the correct answer. Not all NumPy functions know about AstroPy units, but several of the core ones do. The trigonometric ones count. So you can take the sine, cosine, tan, whatever you want, of a number of degrees or a number of radians, and it will do that math for you. You don't have to convert units anymore. If you take the square root of something that has squared units, it will return the unsquared unit. You can quickly generate arrays of values and their mean using the standard NumPy operations that you're already familiar with. You might know that mathematically, you shouldn't be taking the logarithm of something that has a unit. So if you try to do that, AstroPy yells at you. It tells you no more, please. But if you supply it with an argument that can be reduced to a dimensionless quantity, it will do that reduction and then return to you the answer. So hopefully that will do the right thing for you without failing. Now we can take the trigonometric functions. By default, will return just a value, just a number, in this case a float. But you could also tell it to do the operation on what's called a dimensionless unscaled unit, which is to say, this is a quantity that has no unit associated with it. And when you do that conversion, the arc sign is going to return to you the correct quantity in radians, so that it will propagate through those units for you. We can convert that to degrees like so. Now, in-place operations are a bit special. If you try to set a NumPy array to a value, sorry, to a variable, and then you multiply that variable by some other quantity, you're going to get an error. So be careful to avoid that. The way to avoid that would be that you define A twice, basically. So you define A, and then you would set A equal to A times the quantity, which is a little bit clunky, but prevents issues. And lastly, this is not terribly important, but pretty slick, so I'm going to share it with you anyway. We have ways of defining your own units. So say you are a heliophysicist and there's some unit you really care about, you can define your own units this simply. You specify the name that you want to associate with your new unit and its representation in more fundamental units. In this case, a sol is the length of a day on Mars. And then you can convert the number of days in a year on Mars into sols like so. There are also rather radical units like the Pirate Ninja, which is 1 kilowatt hour per sol. You can define that using emoji and it will understand what to do. And you can convert that into watts. Isn't that great? Now, there are physical constants associated. Let's say you have big G. I've forgotten what that is to 4 decimal places, but AstroPy knows it for me. I don't know C to 8 decimal places, but AstroPy does. There are also important radii in astronomy already memorized, so you can convert those into any units that you care about. There are many physical constants already available, and if the one that you need is not there, pull requests are welcome. And finally, for more high energy folks, this example is a little bit fun. Let's say you have the mass of a proton, which is MP here, and you tried to convert the mass of the proton into electron volts. This is something that some people have memorized. I don't. And if I tried to do this, it would fail. It would fail because it thinks that the mass in units of kilograms cannot be converted into electron volts. To specify, I want you to be a bit more flexible and use the rules of physics to figure out how these two units are equitable. You could do that by specifying the mass energy equivalence. This is what that looks like. You would take MP, convert it to mega electron volts, and tell it that mass and energy are equivalent via E equals mc squared, and then you get the answer. The same is true if you try to convert electron volts to angstroms. It says, I don't know how to do that. We could fix that by finding the equivalent units to electron volts and using the spectral equivalency, which uses these rules. It's a little bit unwieldy, to convert from electron volts to angstroms via a spectral equivalency. Then you get an answer. So there are some examples at the bottom. I'm not going to take the time to go through them, but I encourage you to experiment with them later on if you have free time and your mind is not already sufficiently blown. AstroPy units have saved me many a problem set, and I hope they do the same for you. Are there any questions at this point? Yeah. I'll repeat the question so that people online can hear. Does AstroPy units work only with NumPy, or does it work with other packages as well? Short answer is it works with NumPy, but not SciPy, for example. And there are select functions that work the way you want them to, and there are ones that don't. They're all documented on the website. So I encourage you to check out the documentation to see if we've already implemented versions that work for you, but it's not always going to work. One of the tutorials that I'm going to show you in a little bit is how we've developed a table data structure in AstroPy that has a metadata space for units. Pandas does not. And so there is no obvious way to build into Pandas the unit today. Stuart says maybe. Me neither. Yeah. So I would say those things are in development, but what I'm going to propose to you later on is that if units are really important to your calculations, you can use AstroPy tables instead of pandas, and then convert your result to a pandas table very simply. Or vice versa. If you have an output from someone else in pandas, you can convert it to an AstroPy table and then do unitful calculations before returning the result as a pandas table. All right. Taking a look at Slack for a moment. There are a bunch of questions, but I will not answer all of them. Okay, great. So I'm going to move on in the interest of keeping to time. And before I do, I just want to make sure that I'm super mindful of the schedule. So the quick break happens in a bit. We have a while. Okay, good. So astronomy is one of those rich historical fields that has a lot of baggage because it's so rich and historical. And perhaps nowhere does that show better than in our use of coordinate systems because there are so many of them. Fortunately, for people entering the field, you don't have to deal with coordinate transformations too much in your daily life at the very fundamental level because there are packages like AstroPy which can do it for you. One place where this problem is exceptionally challenging is in time. And perhaps one of the places where you've interacted with AstroPy already, perhaps in SunPy, has been through the time module. And we're very proud of the time module because it fills a niche that is very particular. It can specify a time with a precision of a nanosecond over a Hubble time, which is about 10 billion years. There aren't many other time packages that worry about that kind of precision over that kind of duration. But in astronomy, we care. Maybe we care too much, but we do care. And so the time module is built to solve that problem. If you import the time object from the time module, you get access to representations of times in units that astronomers are familiar with, and also more human readable units. And I'll show you interactively a version of this API in just a moment. The main takeaway is that if you are working with someone who operates a spacecraft and they're accustomed to exchanging units with you in Julian date, and you could not be bothered to learn what a Julian date is, you can convert between Julian dates and Python datetime objects, or standard like UTC human readable times, rather trivially with the time module. Coordinates can be tricky because there are so many ways to represent them and to convert between them. For our purposes, I'm going to talk about the coordinates on the sky as though you know my units, and I'm not sure that you will have dealt with them very often. So I'm going to take just a second that I don't normally take in this tutorial to explain. Usually you explain a coordinate on the sky with a latitude and a longitude, And in astronomy, the standard way of thinking about this is RA and dec, which are right ascension and declination. So if you see throughout the tutorial that we describe RAs and decs, those are ways of describing the longitude and the latitude on the sky. Right, and so the most fundamental object in the coordinates module would be the sky coordinate object, which allows you to specify both that longitude and latitude on the sky. It accepts arguments with units, so you can specify whatever units you feel comfortable with. There are also representations of other coordinate systems that are not specific to the sky. So you can say Cartesian representation has an X, Y, and a Z attribute. And so I can initialize a Cartesian representation with unitful quantities along each axis. And it knows how to save and do transformations on that coordinate system. Within AstroPy, there's a lot of machinery for converting between the various types of coordinate systems that exist. So for example, some people who work for ESA do a lot of work with Gaia. Gaia is measuring positions of 1 billion stars. Some of the people who care about those billions of stars care about the fact that they are in the Milky Way, and so deal in galactic coordinates. And other people think about ecliptic coordinates because they're used to observing from the ground. If you want to convert between the two, there is a mapping, but most people don't memorize it. It would be from the galactic coordinates. You might want to get to ICRS coordinates, which you can do via FK5. You don't have to know that. AstroPy does it for you. There are several extra tools that are in there that are pretty neat that I'm going to show you in the tutorial. You can also initialize coordinates and times with arrays or lists, and it will carry them around for you. And let's dive into the time notebook. And so again, if you're navigating through your HelioCloud, if you click on AstroPy tutorial, go to coordinates, which is number 4, and then go to AstroPy coordinates. This will be a very quick tutorial because I recognize that not all of you care about the whole sky all of the time. For those of us who do, we're often querying databases from the astronomical community, which have disparate web interfaces for querying all of the different catalogs of sources in the sky. To handle that, there's an AstroPy affiliated package called AstroQuery, which we will import first. And then we will import a bunch of other packages, including AstroPy coordinates and the table module and the units module. So we can represent times using the time object. The time object asks that you give a value of the time and its format like this. So we can specify a time in units of Julian date. What gets returned to you is a time, which by default is on a UTC scale with the format of JD, given the value that you initialized it with. To convert to the favorite timescale that you use, usually there's an attribute for it already built into the time object. So if you call t.jd, it will give you the Julian date. If you call t.iso, it gives you the ISO formatted time. And if you call t.datetime, it gives you a Python datetime object. If you're not familiar with this, there's a supported built-in package to Python called datetime, which has a lot of functionality for explaining times, even across different time zones. That's very useful. Astronomers care about specifying time in different units via different scales. And so there's a different scale called UT1, which we can convert to by calling t.ut1.iso to get out the ISO formatted time in the UT1 scale. Hi. It should if you specify ISO T. Thank you. And then you can quickly specify times that would be inconvenient to specify with most other packages by specifying, for example, let's take the present time with time.now, and let's add to it an array of times between 0 and 1 days from the present time with 10 elements. And that will return to you an array of times specified that are linearly spaced over 1 day from the present time. So if I really quickly wanted to turn that into units of Julian date, I could do .jd. If I wanted to see what those times look like, I could do .iso. And if your code takes ISO T format, then you just add a T to the end. I'm going to skip over some of this, except to say maybe just the first cell. You can specify the coordinate of an object on the sky by default in RA and DEC coordinates if your frame is ICRS, but that probably doesn't matter to you very much. But the sky coordinate object can take all different kinds of inputs formatted in different ways that astronomers often deal with. And I'm going to skip over the rest of this tutorial because there's a specific Helio related tutorial in this directory that's just for you. So if you take a look in this directory, there's a separate notebook called image coordinates. Which I devised with a lot of help from Will Barnes because this is meant for you. There's one inconsistency in the way that I'm going to present this material to you, which is that there are FITS files and WCS coordinates associated with those FITS files. And I'm curious, because I can teach this in any order that's appropriate for you. I could explain what a FITS file is and very quickly summarize what WCS is, and then show you how imaging coordinates work. Or we can jump straight to the imaging coordinates and then backtrack to talk about FITS files. How many of you know what a FITS file is? Everyone, cool. So we could do FITS really fast, I bet. Let's do FITS really fast. Okay, sorry, I'm gonna backtrack for just a second then. Back in AstroPy tutorial, there is a module called FITS, which is directory 5. In there, there are two notebooks. One is called FITS files and the other is called managing FITS files. We're going to open managing FITS files, which I'm just going to breeze through really quickly. There are many ways to handle FITS files. AstroPy offers you one way. The way that AstroPy FITS files get opened is by opening the IO module within AstroPy, which contains another module called FITS. So from astropy.io, we import FITS. There are lots of ways to open a FITS file. You can do fits.open and then the file name. You can open a FITS file stream this way into a variable called F. We can then print info that is stored within F and then close that file stream by calling f.close. We can see that this particular FITS file contains lots of HDUs in different versions, different numbers of cards and dimensions. One of the neat things about this FITS module is that it can unpack gzipped files, for example. So this is a FITS file that has been gzipped. It does not care. It shows you the contents of the file without figuring out how to untar it. Okay, and we can do the same thing by calling fits.info on the file path. The object that gets returned to you is an HDU list, and we can get elements of that HDU list by indexing F as though it were a list. You can also specify the extension name and version number in a tuple to query specific HDUs out of that list. And f.info does lazy loading. You can adjust that as you see fit. There are a lot of details about working with fits headers in this notebook. And if you're curious how they work, you should read over this section, but I'm not going to belabor it. The part that's relevant to the imaging coordinates tutorial is working with image data. So let's say we have a fits file that we want to open like this. We call the open method on the fits module, and then we pass in the path to the fits file. We can check the contents. This is a 512 by 512 image, which maybe to heliophysicists is a joke. Our resolution is not the same as your resolution. We can check the shape of our science data by taking out the primary HDU by calling F0 dot data. That will give us the data component of the HDU 0. You can also, once you store that science data in an array, you can use fancy indexing in NumPy to access specific rows and columns and then take their mean, for example. We can also plot the science data, which occasionally in astronomy is very pretty. We can do basic array calculations like the min and the max. We can query for specific keyword values in the header. We can set them and delete them. I'm going to stop with this tutorial here and move on to the imaging coordinates one now that we should all be on the same page about how fits files work. Okay, so back in AstroPy tutorial, if we go back to coordinates, we open up the image coordinates tutorial. Often you have beautiful images of the sun and you want to attach coordinate metadata to those images. Or you already have that coordinate metadata specified and you need to read it and handle it and visualize it. And in order to do that, we can use AstroPy and SunPy together, which I'm going to do in this tutorial. So here we're going to first load some packages that should be familiar to you. And then we're going to use SunPy's data module to import an image, an AIA 171 image. And the coordinates module in AstroPy is extensible. So you can create your own coordinate frames in other packages. And SunPy.coordinates has a helioprojective reference frame that you can specify. So we're going to use that. Then there's a bunch of utility things within AstroPy that we're going to use, which I will explain as we go, including from the visualization module. Apologies to those of you who are offended by our American use of Z. Visualization module with a Z will support visualizing astronomical data sets conveniently, hopefully, that's the goal. I'll show you what that looks like in a moment. So by calling that SunPy.data command, we've gotten access to this particular image, which comes from AIA. And if we do fits.open and then imagefile.info, we can see the contents of this file. It is a 1024 squared image. It's compressed. Furthermore, there's WCS associated with this. If you're not familiar with WCS, congratulations, your life has been much smoother than ours. But if you are familiar with WCS, you know that it can give you headaches. And to get around that, there is a WCS module that has a lot of features implemented in it already for you. So you can specify that the WCS associated with this fits file is specified in the header. You give that header as the argument to the WCS constructor, and then you get an instance of your WCS in this variable named W. Here, the units associated with this image are helioprojective longitude and helioprojective latitude. And there are many other keywords here that specify how it works. Here are the long versions of those names, just so you can read them. And there's metadata associated with the number of pixels in your image and the dimensionality of your image. Now, a common problem is that you can easily specify by looking at your screen what the pixel coordinates are of an object of interest or an area of interest on the sun. But your task is to convert that pixel coordinate into a world coordinate, which would be helioprojective longitude and latitude. So we can do that by creating what I'm going to call the hand-selected pixel coordinates, which I obtained by staring at the screen and choosing interesting features on the sun on this day. I can specify the coordinates of those pixels and convert them to world coordinates by calling W, that WCS object, dot pixel to world on the hand-selected pixels. That returns me a variable which I've called hand-selected coordinates, which you'll see is a sky coordinate object, so a position on the sky in helioprojective reference frame at a particular time for a particular solar radius, and then lots of extra metadata before providing us with the coordinates that we were looking for in arcseconds. We can also do the reverse. We can call w.world to pixel, and it will convert those world coordinates in units of arcseconds into pixel coordinates, which gives us back what we started with. Now, I'm going to do a slightly contrived exercise to show you why we like the coordinates module in astronomy. The slightly contrived exercise is to generate a bunch of random points across the surface of the sun. And so you can ignore the contents of this cell except to see that I've created a bunch of random pixel coordinates that are uniformly distributed across the surface of the sun in this image. And then I've converted those pixel coordinates to world coordinates. Let's visualize some of this because everything I've just said to you is a lot of words, but it's easier to see it. So here I'm showing you the image of the sun that we've been working with, that we've been converting the pixel coordinates to world coordinates and vice versa on. And I randomly generated some positions, which are the blue circles, all across the surface of the sun. And I hand selected the red coordinates, which I came up with because I thought they looked pretty. Now, a problem that we often deal with in astronomy is that we have large catalogs of existing positions of objects. And then we have, for example, a smaller catalog of the things that we personally care about. We want to query the large list of sources against our small list of targets of interest so that we can reference the bigger catalog. This happens all the time with Gaia, for example, because there's a billion sources in that catalog. Often we need to do a coordinate match to say, I have targets at these coordinates that I care about. There's a much larger database that has coordinates of many, many targets and other measurements associated with each target. Could you please match on the sky plane the list of coordinates that I have with the list of coordinates that someone else has? So I'm going to show you how we do that in one line using AstroPy's tools. We can specify that our hand-selected coordinates, which are in the world coordinates, should be matched to a catalog on the sky of those random world coordinates, which I specified earlier. This does a match against position for the nearest neighbor to each object on the big table of random coordinates by comparing to selected coordinates, which will return to you an array of 2D separations between the nearest neighbors and the hand-selected coordinates. So this is how distant each random coordinate is that matches the hand-selected coordinates. In other words, what is the closest match in the blue circles to each red circle? So this is the 2D separation in units of arcseconds. And we can plot, for example, just the best matching pairs of coordinates by down selecting. And now I'm going to take a moment to dive into what this block of code does. Yes. So you're referring to this. It says, give me the separation between the hand selected coordinates and the best matching nearest neighbor in the large catalog. If they're not in the same frame, I believe it converts them. I think based on the object that you're operating on. Cool. So I was going to dive in to show you how I make these pretty plots, because by default, your pretty plot won't be quite so pretty. The way that you do that is, yes, question.
Yeah, I just had a quick question about the conversion. Is it a conversion for the smallest or the nearest neighbor on a sphere or a plot?
Sorry, I
This
missed the
approach.
last 3 words.
Is it finding the nearest neighbor on a sphere or does it find it on a plot?
So by default, thank you for this question. This is an important aspect. By default, in astronomy, we're usually concerned with matching sky positions in the sky plane for objects that are basically at infinity. So the function that I used here is match to catalog sky, which says find me the best matching nearest neighbor on the sky plane, which is different from the nearest neighbor on the solar surface, right? That's a different coordinate frame. The alternative that exists within AstroPy is match to catalog 3D, which is irrelevant to your work, I would assume, where if each of your coordinates also has a distance, then it matches against the 3D coordinate between 2 catalogs, which Gaia folks really care about. Yes, Stuart.
There we go. I assume that using match catalog to sky on 2 heliographic coordinates, i.e. coordinates on the surface of the sun, would also work. It's just because it's the same spherical geometry problem. You just centered on the center of the sun, not on the observer. So I haven't tested that, but if you wanted to do angular separation on the surface of the sun, you could use that in heliographic coordinates and it would give you angular separation on the solar sphere.
I hope that it will.
Yeah.
Yeah, I haven't tested that.
Whereas if you wanted to do like spacecraft separation or actual real world distance separation in 3D, you could do that with the match catalog 3D thing you showed.
Right. Any further questions? Okay, great. So I was going to dive in to show you how we actually make these pretty plots, which if you've used SunPy before, you've probably generated with much ease. And to kind of pull back the curtain a little bit and show you how SunPy does that, I'm going to show you how you would construct using Matplotlib and AstroPy a decent looking representation of an image of the sun. To do that, you create a figure object first, which specifies the figure that you're going to draw on. You specify the axis of the subplot that you're going to create. And this is where your WCS information gets written into the Matplotlib object that you're working with. You specify that the projection is equal to your WCS object. There's a lot of magic that happens in here that allows you to get the coordinates of the image to be the helioprojective coordinates that you're used to. Scrolling back up. We can then represent our image data. But if I were to just represent our image data with imshow, for example, and I take our image file and plot it, you don't see anything. And that's an unfortunate property of our data here, is that the stretch of your color bar matters a lot. And so we could go in and we could say, okay, well, I bet the minimum is going to be like 0 and the maximum is going to be, I don't know, pick a value. That was actually not bad. Then you can get an image that looks like the sun again. But it would be inconvenient to come up with every time what your scaling factors are. And it also diminishes your dynamic range. Usually you don't want a linear scaling on these images. And so we can avoid those problems by using some visualization tools built into AstroPy. One is the image normalize object. Image normalize is going to take that image data that I just showed you in the plot before and assign to it an interval, which is between the maximum and minimum pixel values. And then here we're using the hyperbolic sine stretch with a given scaling factor, which produces images that are what you're accustomed to, I think. Then to tell ImShow how to normalize that image correctly, we do ax.imshow on the image data, and we specify the normalization by saying norm equals norm. We can then use scatter points to represent the hand-selected pixel coordinates. And we can plot the best matching random coordinates, which came out from this special index variable. Index was one of the outputs of our matched catalog. And if we print index, you will see that it is the best matching index of the random world coordinates that matches each hand-selected coordinate. And so when we make this plot, we get a nice looking plot of the best matching coordinate on the sky plane between the hand-selected coordinates in red, the random coordinates that best match them in green. And we can specify coordinates a slightly different way. Let's say it was convenient for you to specify a solar coordinate in helioprojective units because someone gave you that. And then you wanted to convert that to pixel units to plot in Matplotlib. You could specify that the solar origin is at 0, 0 in the helioprojective frame, like this. And then we go through the same exercise of generating a Matplotlib plot of our solar image. And then we can call on that solar origin that the longitude and latitude of our point at the solar origin gets specified like this. We would do solar origin.tx, solar origin.ty, which specifies where the solar origin is in pixel coordinates via a particular transformation that coordinates from the helioprojective frame to the pixel frame. We do that by saying transform equals x.get transform world. Don't memorize that, just have this notebook around if you need that. And then you can easily specify positions on the sun in whatever coordinate frame you care about, and then plot them. I suspect that in the SunPy session to follow, there will be much easier examples of how to do this without worrying about all of these details. This is just to show you what's going on a little bit beneath the surface. To make what? This one. Yeah. That's right. There's more than one way to do it, for sure. Are there any other questions here? Okay. Question in Slack. How would you transform a vector, for example, a magnetic field vector, at a point instead of a position? Great question. I don't know if there's a simple answer to that question. The simplest answer that comes to mind is already mentioned by the person who asked the question, which is that right now, sky coordinates can also represent velocities. And so you could have the 3D position and then a 3D velocity of your target. And so you could, in principle, choose to represent things that way, but I wouldn't recommend it. For Eric's benefit, Stuart knows the answer to your question, but does not know how to answer it right now. Any further questions? We're a bit ahead of my schedule. Are we already overwhelmed with astronomy? Yes. Okay, cards and FITS files. Glad you asked. So storing metadata in a FITS file has some peculiarities to it. One is that FITS file header is basically a dictionary, but the keys in the dictionary, the key value pairs in the dictionary are referred to as cards because of history. Because FITS files are well worn, put it that way. So yes. Does AstroPy do anything with binary tables and FITS? Yes, it handles them. And so does the table module within AstroPy. So you can read binary tables to NumPy arrays through the FITS module. And you can also read binary tables to any other kind of format that you can imagine via the tables module. Any other questions here? All right, great. Just to be sure that I'm on time, we have a coffee break in 15 minutes. Is that right? Yes. Okay. So at this point, so I don't overload you too much, I'm going to go back and suggest that you take a moment to go back to the units examples because we have the time, and I will walk around. So for those of you following along, if you're in the AstroPy tutorial top level directory and you click in units quantities and you click in AstroPy units, there is a notebook which I walked you through earlier. Down at the bottom, there's a section that says putting it all together that has examples that I skipped over that I would like you to do until the coffee break. So feel free to experiment and ask any question that comes to mind. If you raise your hand, I'll come over. Happy to chat with you. All right, so we have 2 minutes left, I believe, before our quick break is scheduled to occur. And I've been corrected. It is a quick break, not a coffee break. So if you go looking for coffee and don't find it, that is my fault. I apologize. But before we jump to quick break time, I'm going to show you the answers. In this same directory, there's a separate notebook called AstroPy Units Solutions, because like any good chef, I've prepared the meal for you in advance so you can see the finished product. So let's look at exercise 1. The goal here is to figure out how far away the James Webb Space Telescope will be at the time this was will be, because it hadn't launched when this was written, or presently is, from the Earth or from the sun, for example. So we can import AstroPy units. We can specify the distance from the Earth to JWST is some number of astronomical units away, which comes from the equation that was specified above. So the distance to Earth is the mass of the Earth over 3 times the mass of the sun, quantity to the 1/3 power. That will save the distance from the Earth, and we can convert it to kilometers, yes. Thank you. This question is, why do we need this 1 here? But not elsewhere. If I remove that 1, it's still going to work. The reason why we keep it there is kind of pedagogical, which is to say that we want the quantity and not the unit here. Why you don't need it here? You don't need it here or here because a quantity is specified here. Exactly. If you have 1, they all become quantities. That's right. Yes. If you use what from the constants? Sorry. Oh, I understand. So there are 2 ways to get the mass of the Earth. One is u dot m Earth, which gives you the mass of the Earth. The other would be from astropy.constants import m Earth, which also gives you mass of the Earth. The difference between the 2 is that this is technically a unit, and this is technically a quantity. And we can check that. So the quantity is a constant. The reason that there's a constants module is partly for documentation purposes, because if we check what m Earth is, it will actually give you a reference for where this mass of the Earth or radius of the Earth came from. That's one of the motivations for creating a separate class of things. In practice, they should be identical, right? So if we check mass of Earth is equal to u dot mass of Earth, does that work? Yes, that works. So everything's fine. Whew. And the distance in miles, we can convert with a little extra step, just so that when you communicate with the public, you know, you're careful. And then exercise 2 is saying L2 is 1.5 million kilometers away. The total mass is very small compared to the sun. Using the value you obtained, compute the force between James Webb and Earth and James Webb and the sun. This is simply to demonstrate that you don't have to propagate the units, not that this is calculation most people think is terribly important, but we can import big G. We have the mass of the Earth as a unit. You know the mass of the spacecraft and the distance to the Earth. If you were to simply print F, you would get a number with crazy units. But that force has units of newtons as long as you ask it to convert to them. And we can do similarly to measure the force, the other force, the force to the sun. All right, it is quick break time. you've all made it. If you have further questions, I'll come to you and we can chat during quick break. Thanks for your attention so far.
I feel like
All right, welcome back, everyone. I hope you are rested. You are braked. You are ready for more AstroPy. Yeah? I'm gonna hype up the crowd. PyHC. Yeah. Okay. Can you tell that I did astronomy on tap in my city? That's what I'm used to. Okay. So I'm going to cover at least one more pre-written module. And then I'm going to give you 2 quick summaries about the community and contributing to AstroPy, which I hope is entertaining and interesting for you, and also less pressure than running code and making sure you understand how every line works by listening to that session. And then I want to save just a little bit of time for interactive Q&A. I can't promise that I know every single function in AstroPy, but I can try to point you to the correct places in the docs to answer the questions that you might have about how AstroPy can work for you. So to begin, let's do some tables. So in the AstroPy tutorial directory, there is a subdirectory named tables number 6. You click on that and then open the tables Jupyter notebook. You will navigate to the notebook that I have open. Now, you may be looking at me and wondering why I'm going to talk to you about tables. And the reason for that is partially evidenced by half of the questions I've received in the last 10 minutes, which are mostly, okay, units, I get it. I get why we need them. They're great. I want to use them. But now I have a billion measurements that each have different units associated with them in a giant table. How do I coordinate the usage of those units with many values that I want to do calculations on? The short answer is that AstroPy has developed a unit system that is not compatible with every table package. For example, you might be using pandas data frames to represent your tabular data, which is awesome. If you're already doing that, that's awesome. We love pandas data frames. There's currently the easiest way to incorporate extra metadata, including the unit, onto the quantities that you have measurements of, is going to be to use AstroPy tables. What do they do? Well, they allow you to take in data from a wide variety of sources that are formatted in many different ways and read them into one unified data structure. They allow you to modify the tables relatively conveniently. They allow you to handle tables with missing values, as well as extra metadata that you want to incorporate into your data. They allow you to specify units on columns. That would be the biggest single feature that I want to advertise in this portion of the talk. They contain some operations on tables like joins and grouping. You can have multi-dimensional columns. And there's a really robust infrastructure for writing out tables in different formats, which I will demonstrate. Now, if you're already comfortable with data frames, why should you use AstroPy tables? Again, the short answer is units. It's easiest to represent units in AstroPy tables. And we love data frames in AstroPy table world. So there are convenience functions for reading a pandas data frame into an AstroPy table and for outputting an AstroPy table into a pandas data frame. So you can convert back and forth when it's convenient for you to use one data structure, you just switch. There's more color in the description over here that you can read if you choose. And of course, there's loads of documentation. But let's begin with some code. So the AstroPy table object is accessible from astropy.table import table, following the pattern that we've established so far. There are many ways you can create a table object. Here's one way. You can create a table instance like this, where you just call table with empty parentheses. That creates a table object called T. Within T, we can create a column called name, as though we were accessing a dictionary. And then we can create the rows in the name column by supplying a list to the right-hand side of the equals. You can do the same with numbers or strings or various data types. And now we can inspect that table by just looking at the output of T. By default, in a notebook environment, it's going to render your table with HTML, which is pretty snazzy. And then you can print your table in plain text by printing the table object. That's how it would appear if you were doing this on your terminal. You can inspect the names of each column with .colnames and the data type of each column with .dtype. And there's a handy function called show in notebook that has more interactive features, especially when your table is very large. We'll show you an example of that. There are many ways to access elements within your table. So let's say you want the flux column. You call flux as though you're getting the column as the value with the name of the column as the key in the dictionary. That returns to you a column object, which is basically a thin wrapper around a NumPy array. So we've got a NumPy array representing the numbers, and then we've got metadata, including the name of the column, the data type, the length, and optionally a unit. We can get the 1th row, which is the second item, out of the flux column by calling T brackets flux and then brackets 1. Alternatively, if we called T brackets 1, that would give us the first row and each column. We can achieve the same result as calling T flux 1 by calling T1 flux. And you can also query with slices. So you can say, give me the 1th to the 3rd row. It will do that. And you can give it a list of rows, and it will give you the rows that you asked for. This becomes useful when we generate masks with indices. So for example, let's say we wanted only the fluxes that were greater than 3. We could create a mask variable, which is a NumPy array of Boolean objects, so trues and falses, where the flux column is greater than 3. And then we can ask for just the rows which meet those criteria in the mask from the table by calling T brackets mask. And that will return only rows where the flux was greater than 3. Just to prove to you that that makes sense, mask is an array of trues and falses, which is true where flux is greater than 3. We can modify the table like this. If we want to add a row, you call t.addRow, the name of the row that you want to add, and its value in each column. If you want to add a column, you do so like creating a new key value pair in a dictionary. You specify the name of the column that you're creating and its value, which in this case is going to be the vector of the log base 10 of the fluxes. By default, it's representing the log 10 of the flux with precision, perhaps too much precision. We can get rid of that with the format attribute. So if we tell it that we want to format the fluxes to be 2 decimal places and the log flux to also be 2 decimal places, then it will represent the table in a pretty way. This becomes more useful, again, when we specify units. You can specify units using their string names. So this is in Jansky's, which is somewhat astronomical. So we can specify that the unit on the flux column is this. which then adds an extra layer of metadata in our table when it prints it out, so that you can see that each of these fluxes has a unit of Janskis. And if we do T flux, we can see that there's extra metadata for the unit in there, as well as the format, which we specified. That will come in handy later. Now, reading tables, ideally, is easy. And you can do so with table.read and the path to the table that you want to read. Let's say there's a binary table in a fits file that you'd like to read. If you call table.read on that fits file, it will read that table for you. So here are the names of the columns, here are the data types, and here are the values. Sometimes you have to specify the format of the table that you're reading if it cannot figure it out for you. So example.dat is an ASCII file, and we can specify an ASCII file with this format key, which gives us the same table that we just read a second ago. You can also read CSV files with ASCII.csv. And there are some scary formats of data that we deal with in astronomy, like IPAC tables, which you can read rather easily as well. This is my favorite part of the entire AstroPy tutorial that I'm about to teach you. Hold your breath. This is where it gets crazy. Okay, ready? So let's write a table. It's a problem you've probably solved 10 times. If you do table.write, the path to the file that you want to write, the format that you want to write it in, and optionally you can specify that overwriting the file is okay. It will write the plain text representation of your file, of your table to a file. That's cool, right? But it's not a big deal. We're going to get to the big deal. Then, if we have table.read on test.txt, we get back the same thing that we started with. Isn't that great? But we've lost units because a CSV file does not have a standard specification for units. The way around this is that there's such thing as an eCSV file, which contains extra metadata. And so if you write your table to an eCSV file, and then you read it back in as an eCSV file, you recover the Jansky units that we put in the first place. So that's still human readable and round trips correctly. Suppose you want to write a fits file with your table. You could do that with t.write test.fits, and it understands what to do. You can also write things like VO tables, which some people like. But here's my favorite part, okay? So let's say you have a table and you're about to write a paper with your table's information. Wouldn't it be amazing if you could just say, for example, that the format should be LaTeX? And then check that your LaTeX was correct. Thank you, folks on Zoom, for paying attention. This works with big tables. That blew my mind. Okay, but back to the main stuff, right? Because that's not astronomy or heliophysics, but that gets us excited, right? Okay. So we can also store more complex data. For example, times. So let's represent some times, which are starting at the present time and then going back 2 hours, 1 hour, and 0 hours. It's a funny way of saying the last 3 hours. And then the fluxes in units of magnitudes. For those of you used to the sun in apparent magnitudes, it's like that, but with the negative sign missing, right? We deal with faint things. And then you can represent a table with the time of observation as an object, where that object is a time object. So all we've done is we've specified the names of the columns here and the data that goes into those columns. And it understands that there are units on the flux object and that the time object, the time column is special. It is an object that is a time object, which means we can do operations on that time column. So we can say, what is the JD equivalent of each row in the time column by calling the time column.jd. You can also do operations with units on the unit full column. And finally, just a little word of warning. If you access a column object is not the same as a quantity. There are reasons for that, but the upshot is that if you check what this is, right, it's not going to be a quantity. There's a way around that. In AstroPy, there's a table called a Q table, which is a quantity table. And what that does is when you ask for a specific column, it returns to the quantity object that that column refers to. So subtly different, but importantly different. And then just to demonstrate that some of the things that you like to do with tables are already implemented in AstroPy, we can do a table join. So let's say we have this table with a bunch of strings and then fluxes and log fluxes. We can get additional values that sometimes overlap with the previous ones, but not always. So there's a row for Larry, Mo, and Groucho, who does not appear in the original table. They each have measurements associated with them called flux2. We can then join these tables in a somewhat intelligent way by using the join method in the table module to join table 1 and table 2. We want the keys, the parts that are conserved across both tables, to be in the name column. We're going to use join type outer, which says if you're missing part of one table, when you incorporate data from the opposite table, then put in a masked value where there's missing data. And so what you get is a list with every name that appears in either table and masks where there is no data from the opposite table. And then you can do intelligent things like measure the mean of flux2 across this join table, and it will skip over the masked values. You can also do a join type inner just to demonstrate the opposite, which is where the data overlap between both tables, return all values, but otherwise ignore them. You can also carry around masks on AstroPy tables. So this is a masked table because we've set masked equal to true. We can set the value of the mask by accessing the mask attribute of the value column, which we've set to false, true, false. And now if we print the table, you can see that the mask being true has masked out the value for y. And then you can do things like setting a fill value so that it fills the masked values with some predefined magic number, for example. And I promised you that you can interface with pandas. Here's what interfacing with pandas looks like. If you have a big table, which we've read in here, this is a table from 2MASS, which is an infrared sky survey. And you can see there are 1,000 values in it with their own coordinates and brightnesses and flags, extra data, which contain things like units. So the coordinates have units of degrees, the error has units of arc seconds, the brightnesses have magnitudes. So it's a complex data set that's well represented by an AstroPy table. If we call this table object dot to pandas, we get out a pandas data frame that looks just like the AstroPy table. And then we can demonstrate that the round trip works if we do table.fromPandas, initialize with the pandas data frame that we just specified. We get the AstroPy table representation again. The one difference here is that there's now an index column that goes between 0 and the number of data points that you have. And this table is very long. So there is a trick that I'm not remembering at the moment to display this in a short form. Yeah, if you do show in Notebook, it doesn't abbreviate the table, but if you just plot the output, sorry, print the output, it does clip it just a little bit for you. And then there are features that AstroPy has not taken the time to implement that Pandas has. So sometimes it's advantageous to take your AstroPy table and convert it to a Pandas data frame so that you can exploit things that are implemented in Pandas. Like, for example, we have not figured out how to write Excel files within AstroPy because Pandas does it very well. So you can do the Pandas data frame to Excel, which is a Pandas method, to write it to an Excel file. We also haven't bothered to learn how to read Excel files within AstroPy, but Pandas does that very well. So you can then read your Pandas Excel file into an AstroPy table by calling the Pandas data frame into from Pandas. And then that does the same thing again, this time going through Excel. So all of that to say, for example, if you have a CSV file with like 1 million or 10 million rows in it, it might not be convenient to use AstroPy's table.read method because it might not be as efficient as Pandas. But if you read it in Pandas and convert it to an AstroPy table, that sometimes is faster. So we are very cognizant that we live in a world where Pandas exists, and we don't want to ignore it because it's really great. Because you can do things like this. Let's make a scatter plot of the J magnitude and H magnitude, and then you get a color diagram. That's awesome. So let's use their syntax when we can. There's an exercise below, but I'm going to skip it because it's pretty astronomical. And I'm going to stop for a moment to take questions. Are there any questions? Can you use rolling windows in AstroPy tables? We're working on it. Like in a time series, are you thinking, for example? Yeah, so there is a time series module in AstroPy that allows you to do these operations built on AstroPy tables. So I would recommend that you take a look at the time series docs in AstroPy. Personally, I've found that I can use Pandas to do that sometimes more efficiently because we're still developing some of the tools that you need to do that in AstroPy. So it really depends on the calculation that you're doing. Agreed.
There was a question in the chat. How do you create a reader for a custom ASCII format or other binary format into a table?
I'm so glad you asked. If you read the AstroPy docs, there is explanations on how to do that. I recommend you check out the AstroPy docs on the table module. All right. If there are no further questions on tables, I'm going to let your brain take a break because it's the first day. I know a bunch of you traveled, probably already a little bit sleepy because we're not on a Spanish time zone yet. So I'm going to take a moment to share with you some of the information about the AstroPy community that we're very proud of, that we like to share at these workshops, and hopefully welcome you into that community briefly. So there won't be code in these next few slides. This is a little reprieve for your brain before we take our coffee break, and then we dive into SunPy, and then things go on a rocket ship to the sun. So there are many ways that you can stay in touch with the AstroPy community if you want to. The traditional ones are that there are email listservs that you can join. We have a Slack team. You can join our Slack team, and you can be privy to all of the discussions about what happens about designing for AstroPy, maintaining AstroPy, problems that people have experienced with AstroPy, and friendly conversation with people like me. You can find me on the Slack. We also have quite a few different means of accessing learning materials for AstroPy. One is the documentation webpage, which would be docs.astropy.org. Another that I would recommend is learn.astropy.org, which has some tutorials that are really great for the pedagogical side of learning how AstroPy works. If you're into Facebook, there is a Python Users in Astronomy Facebook group, which at first sounds a little funny until you realize how active it is. There are thousands of users. And so if you ask a question, you get an answer pretty fast in that group. And there are a bunch of conferences that historically have been close to the AstroPy dev community. There's organizations like Open Astronomy, which fosters open software and open development in the astronomical community. There's a Python in Astronomy conference series, which is really fun if you're on the astronomical side. Dot Astronomy, which is kind of the interface between the internet and astronomy. And Astro Hack Week, which is lots of fun, lots of developing. At this point, I'm going to shift over to the last bit, which is kind of your invitation to get involved. The AstroPy core package to date has more than 400 contributors. We are very proud of that number, and we want it to be bigger. And I'd be willing to bet that you folks are qualified to make a contribution. And so we want to welcome you to contribute to AstroPy, because it would not exist if not for people like you who have made contributions over time. Contributions don't strictly mean code. There are many ways of developing, of contributing to an open development framework like AstroPy without actually writing software. And that includes changes to the documentation, which are exceptionally helpful from people who are new to the AstroPy community, because you know the weaknesses in the documentation better than we do. But also developing tutorials so that like-minded people can have access to our community, and reporting bugs. If you come across any bugs, we want to know about them. Here is a screenshot of the GitHub page for AstroPy, which looks rather different today. All of our development is done on GitHub, which I think is no stranger to most of you. We have lots of issues. Normally, when people bring up this slide, they get kind of bashful about the issues, but I'm really proud that we have more than 1,000 issues, because that means people use our code and find problems. It's not great that they're finding problems, but it's great that people are using our code. We're very proud of that. So if you check today, there are 66 active pull requests and 1,000 issues to date, generated by more than 33,000 repositories that use AstroPy and 419 contributors to date. The way that we manage such a large community without actually managing anybody in particular within the community is via GitHub. That allows us to track issues, to track feature requests, and questions about how to use AstroPy or why AstroPy might or might not be the right tool to use in a given circumstance. If you find yourself with any of these issues, you can post them in the issues channel on GitHub. You can create a new issue by clicking the green button in the upper right, and very quickly, someone will come along and add labels to your issue. The labels are often very informative. So they'll tell you, for example, that this issue is related to the documentation, it's low effort to fix, and it has to do with fits. And this allows you to quickly search through issues to find issues relevant to your issue if you also have a problem, but also makes triaging easier when you're the person trying to fix an issue. Here's an example issue from Adrian, which says, I can make an enhancement. This is what it would be. And then ideally, issues like this lead to lots of discussion. So if you take a look at this, this has been discussed quite a bit. Pull requests are the place where you contribute code, where you fix a bug, where you edit the docs. And if you've never dug into one before, here's an example pull request. If you click on files changed, you can see a diff between the previous version of the code, which exists in the repository, and the version that someone is suggesting. This is how we check by eye that people aren't contributing nonsensical code. And then, of course, we can leave inline comments on every contribution that someone makes so that we can improve what they've suggested or better understand why they suggested what they suggested. Of course, all of this is enabled by CI. If we didn't have tests to run, yeah, this is old. This is really old. If we didn't have tests to run, then we wouldn't know for sure that the software is going to continue to work into the future. And so if we go to a more modern pull request, for Stuart's sake, before he has a heart attack, if we go to a more modern pull request, you'll see that way down at the bottom of the pull request, there are many tests that get run. They look different than the one that I just showed you on the slide, but only if you're used to staring at these tests. And once the tests pass, a human can click that they approve. In this case, it was Stuart. Go figure. Yeah, you approved this one. And this framework allows us to accept contributions from 400 contributors methodically and consecutively, which is a challenge when you have that many people doing different things at the same time. I mentioned earlier that there's this concept of affiliated packages, and we like to foster development within the broader ecosystem that depends on AstroPy, but maybe doesn't belong in AstroPy core. And that model has been taken up by some of our cousin packages. And so the goal is really to make AstroPy as useful as possible to as many people as possible, and then to foster an ecosystem that depends on AstroPy. And I'm just going to close with a slightly philosophical soapbox, which is that if you want to contribute, these are some guidelines that you can follow to contribute efficiently. For example, if you have a problem, search through the issues of the repository that has the problem to see if someone else has had this problem before, because with AstroPy, there are many problems that people have come across in the past. There are 8,000 closed pull requests and 4,000 closed issues. So there's quite an archive to go through. Then there are coding practices that we try to follow in AstroPy. They're not as rigorously enforced as in some other packages, but we do try to keep the style relatively uniform so that you can read any part of AstroPy and understand what's going on. So if you can adhere to those practices, there are pages within the docs that explain what our style is. We appreciate if you can try to follow that. If you don't, we will leave inline comments and suggest how to improve it. Generally, in your Git practices, it would be great if you had a fork of the repository that you're working on, like AstroPy, and then you created a branch where you implement a specific feature on your fork and give it a good name. All of these things make it easier to manage when you're scaling up and you have a big package with many simultaneous changes. In general, it's great if you can make contributions that can be diffed. So if you want to leave a fits file in a repository, that can be problematic sometimes. But if you want to leave a CSV file, that might be less problematic. So keeping an eye on that is important. And lastly, if you want to create tutorials like the one that we just went through today, it's best to clear the outputs of your notebook because the outputs often take up many lines of your raw text file. And we don't need that in your Git repository. So clearing your notebooks before you output them gives a good user experience to folks like you. So if you're creating your own version of this, that's how we try to go about doing it. We've had a few minutes of space since I showed you code. I would love to ask if you have any questions. I will warn you, I'm very good at awkward silences and I can stand here for 15 minutes. It is in your best interest to ask me a question. So, with that, what are our questions? I'm also watching on Slack. Yes. So this question is for the people online. I'll repeat. What's up with fits? That's the short version of the question. And there's a lot up with NetCDF. So different domains have found many reasons to use different file formats, and geo folks love NetCDF, for example. The statistical inference community recently has taken up NetCDF as its own as well, because we have multi-dimensional data that you need to index efficiently across multiple indices. So NetCDF is not going anywhere, but it is most useful when you have ND data. And usually an AstroPy table, for example, would be just a table. And so it's not necessarily solving the same problems, if that makes sense. An AstroPy table is really just a table, whereas NetCDF can represent 5-dimensional cubes, right? So I would say they solve different problems. Yeah.
A question about the integration of VO table. You said that some people like VO table. It seems that maybe you don't like it. I remember a few years ago when we had the astronomy virtual observatory meeting in Paris, there were some folks from AstroPy. I don't remember you were there. Sorry if you were. And we had some discussion about improving the integration of VO table. And VO table is used in Heliophysics in many services. So what's the status of that?
That's a big question that I don't think I'm qualified to answer.
Okay.
But I will say VO table is the de facto standard for some transactions between data and users. And so we wholeheartedly support the folks who need VO table. For example, I often need filter transmittance curves for astronomical filters, and that information comes from an API that gives VO tables, and I rely on that. And so when I need to read a VO table, AstroPy handles that very transparently without much input from me, which is how I like it.
Yeah, my comment was more on the, so I agree that I do the same, but when I want to write a VO table in a script, which then I want to input to another service, yeah, sometimes it's not so well integrated. There are things that that used to be missing. I have to check maybe if it's if it has been included or not.
Right. So there is a VO table writer in the AstroPy table module.
My info on VO table is a couple of years outdated at this point, but I know that people are working with AstroPy to write PyVO and various other things. So I think there is effort going on there, but whether it like has the features you need now or not, I have no idea.
John Vandegrift asks on Slack, how does the time system in AstroPy handle leap seconds? You are asking the correct nerd for this question. Okay. So for those of you who don't know, the Earth is spinning. The Earth spins with uneven intervals in time because things happen on the surface of the Earth that change the moment of inertia of the Earth, change the spin rate of the Earth as a function of time, and they're stochastic. So you can't predict how the rotation rate of the Earth is going to change as a function of time. Now, you might say that's not a problem, right? Because the Earth is spinning, we can just measure the positions of really far away things. And when they return to the same place on the sky, we've gone through a day. But is that a day? Because really a day should be 24 hours times 60 minutes times 60 seconds, right? If a second is the fundamental unit that makes a day. Well, there's a time scale for both types of systems. There's one based on the rotation of the Earth, and there's one based on the number of seconds in a day. That's the difference between the UTC and the UT1 that I was showing you earlier in the time module. Now, that's not enough, right? Because the Earth's rotation rate is changing. So we need to give little fudge factors here and there to make the Earth's rotation rate match up with the passage of time, which is inexorable and intangible and probably artificial. But the point, not to get too metaphysical, is that if you have a leap second, which happens on occasion, there is a table that is served by the US military. I'm not making this up. There's a table
On a really bad server that likes
on
to
a server
break
that hasn't been
regularly.
maintained for maybe 2 years at this point, which tells you the precise rotation of the Earth as a function of time and any planned leap seconds that are coming and leap seconds that have happened in the past. AstroPy has machinery to automatically download that table, of course, assuming the server is working, which is beyond our control because we have funding, but we're not the US military funding, right? And that service, when it's working, provides for us the predictions of upcoming leap seconds, as well as previous leap seconds, so that you can always convert between either system to account for the rotation of the Earth. So how does, the short answer, how does time in AstroPy deal with leap seconds is it looks up from a table, which is considered like the canonical source of where leap seconds are stored, and handles that for you. So if you are using a time system that has the leap seconds in it, it will add or subtract the second where it needs to be added or subtracted. This is a headache for folks in AstroPy, for me in particular, because leap seconds are annoying. And we needing to rely on the US military to tell us when they're happening is annoying. But the system mostly works, I'll say. I think there's only one, right, I think there's only one official source of the leap second. There might be. I don't know. I was just curious. Yeah, well, you would think the US military could be reliable, but
I think there's an open issue on AstroPy. So if
That's
you
right.
have thoughts about where else we could get them from, putting a comment on there would be useful.
that's right. There are several issues on AstroPy that you can join the conversation on if you have a better alternative. We would love to hear about it. So right now, the solution involves caching a version of the table that has a snapshot of all of the known leap seconds, which goes out of date if the server never updates, which is what's happening right now.
Another online question. Do the mechanisms for adding a day, et cetera, take leap seconds into account?
That depends on the time system that you're using. So if you're using a scale that has leap seconds, be cautious. I'm not sure what else to add to that, and also be correct.
Also, unlike date time and things, AstroPy's string parser will handle a 60th second in a string and vice versa. A 61st second, I guess.
Right. So the goal of the time module is to work. And that is an ambitious goal, right? Because time is messy. But if there's something that you need better handling for, if there's a feature that's missing in the time module, we'd love to know about it. Because we know that you use times in your work all over the place. So we would be super happy to help write the features that you need for your work. Fair, no. How are we doing on early break? Okay. If there are no further questions, because I could stand here for the next 20 minutes and wait for you, but I could also let you go have coffee. If I were to ask for your vote, I'm gonna bet you'd want coffee. Is that a fair bet? Okay, then I'm going to thank you for your attention. Thank you for sticking with me. If you have any questions, I'll be around and I'd love to chat with you. Thanks again.
What?
we're gonna go ahead and start again. I hope you all had a great break. Got some sunshine. We're picking up after the break with the SunPy presentation tutorial given by Will.
Thanks, Julie. Everyone hear me okay? Great. All right. My name is Will Barnes. I am a postdoc at American University and NASA Goddard over in DC in the US. I'm going to be giving the SunPy tutorial along with Stuart over there, who's at Aperio Software over in the UK. And I will say that, we're giving the tutorial, but this is kind of on behalf of the entire SunPy community and the many people who have contributed to a lot of the tutorial notebooks that we've developed for past workshops as well, particularly several of the people that are listed on this slide here. So what I'm first going to do is kind of just give, similar to the structure that Brett followed in his AstroPy talk, give a basic overview of what is SunPy, and then kind of give a brief overview of what we're going to cover in this tutorial. So the first thing is, yeah, what is SunPy? So the SunPy package itself, the actual Python package, provides ways to access and load and manipulate solar data. So our tagline is often it's a package for solar data analysis in Python. And it kind of came about as the result of wanting to, for one, make the transition so that in solar physics, a lot of our software traditionally has been in IDL, not unlike the astronomy community or a lot of areas of the heliophysics community. There's an effort kind of about a decade ago to kind of move towards Python for various different reasons that we won't touch on for now, but also to leverage the powerful scientific ecosystem that was kind of spinning up around that time. So the SunPy package itself provides kind of three main covers three main areas of functionality. So these are the ability to search for and download data. It provides some basic data containers or data structures for things like image data, or we usually call them maps, as well as for time series data. This is probably for a lot of folks that are interested in situ data. This is probably the format that you're used to working with as well. And then lastly, we cover coordinates. So Brett talked a while about AstroPy coordinates and the AstroPy coordinate stack and the kind of powerful functionality that provides for defining coordinates, in particular coordinate systems, and then doing transformations between those coordinates. So SunPy extends that framework as well, and Stuart's going to talk about that in a bit. So this is important, for example, when we have spacecraft that are observing the sun at different locations. So maybe something like the stereo spacecraft, which might be separated 30, 40 degrees from Earth at any given point. We want to be able to do coordinate transformations between those different coordinate systems. So this is kind of what the SunPy package, the Python package itself provides. So similar to the separation or the description of the AstroPy that Brett provided, we have the SunPy package itself, and then there's the broader SunPy project. So the SunPy project includes the SunPy package, as well as various affiliated packages within the ecosystem. And so this diagram just kind of is to illustrate that. So I do want to emphasize too that SunPy heavily depends on AstroPy for various things, from reading FITS files to making use of units and coordinates and constants. We really strive to not reinvent the wheel where AstroPy has already made a lot of progress, and to rely on it whenever possible. And so for things, so like I mentioned, for the SunPy core package, we try to it offers this ability to download data, to kind of load data, and then to do these coordinate transformations. But of course, there's a lot of other things, more either analysis specific things or tasks specific to a given instrument that you might want to perform that are not covered by that scope. And what we try to do is offload those more specific tasks to what we call affiliated packages. So this might be things like doing a field extrapolation, say from magnetogram, a potential field extrapolation, and that for example, that's covered by this package called PFSSPy, which is a SunPy affiliated package. Or you might want to perform tasks specific to AIA data, things like correcting for how the instrument has degraded over time, or looking at the response in a particular at a particular bandpass. That can be done through instrument specific packages like this one called AIA-Py. That's an affiliated package, but also maintained by the instrument team that runs the AIA instrument. So this is just to kind of give some context about what the SunPy project is, and then what the code itself is. Similar to Brett's description of the AstroPy project, SunPy is we try to be very, very open in the way that the package is developed. So all of our code is on GitHub. All of our development is done on GitHub and in the open, and that we really strive to develop the software in such a way that involves the entire community. We don't want this to just be an effort of a few maintainers. We want the community to have buy-in on this as well, and I'll touch a little bit more on that in a bit. So when it comes to this tutorial, what are we going to do? So we want to illustrate kind of these kind of three areas of functionality that the SunPy package provides. Getting data, loading it in, doing something interesting with it. By looking at this particular CME that was observed on March 28th of this year. So this is a LASCO coronagraph image that just shows, you can kind of see from right where my mouse is right here, you can see the CME taking off, and you can see it in the core 1 and the core 2 images. But what we're going to do is we're going to look at this observations of the CME from the perspective of AIA, from the EUVI instrument on the stereo spacecraft, and from the EUI instrument on Solar Orbiter. And so what's interesting about using these three spacecraft in combination is the relative positions of these spacecraft. So this is a snapshot from the Solar Mock tool, which you're going to hear more about, I believe, on Thursday, later in the week. But I stole a snapshot really quick to illustrate how useful this tool is, and also to show. So this green dot here is Earth, which is essentially the location of the SDO spacecraft for which is what the AIA instrument is on. The red dot shows the stereo spacecraft, and then this blue dot, very close, much closer to the sun, is Solar Orbiter, which is where the EUI instrument is on. So what we're going to have is an observation of the CME from these three different perspectives, and you can kind of see that the stereo spacecraft and the Solar Orbiter spacecraft are separated by 90 degrees, which gives us a really interesting vantage points for looking at this event. So we're going to divide this into three components, three separate notebooks, which should all be in your folder on the HelioCloud environment. So if you go to, probably most people have already done this, I should have started with this, but under the SunPy tutorial, all of these notebooks, including this one I'm showing here, just with the intro material, are in this directory here. And you'll see there's, for each part, there are two notebooks. One it has a title and says dash instructor. What all that means is that throughout this set of notebooks, we're going to have a set of exercises that are denoted by these big orange blocks. The instructor notebooks have basically the solutions to those exercises. So it's probably more instructive for you to start with the ones without that instructor label on the end, and then I'll pause and we'll try to fill in those. I'll give you a few minutes to kind of think about that exercise, and then we'll kind of go through the solution together. Okay. Again, and so these 3 notebooks that we're going to do are going to emphasize these 3 areas that I've talked about. Getting data through search and download, loading our data into map and time series containers, and then using the coordinates framework to do some analysis of this event. And again, so please feel, Stuart and I are both going to kind of tag team this presentation of these notebooks. So feel free to, obviously raise hands, shout questions at us when you have them. One last thing I'll note is that a couple of resources that may be helpful either during the workshop or afterwards. We have a web page at sunpy.org that gives, it kind of provides a landing page for the documentation for our core package, as well as all of our affiliated packages, and then gives some like higher level information about the project also. There's our documentation. We also have a list of some tutorial notebooks that we did from a past AAS workshop that this tutorial is sort of loosely based on. And then two things I want to highlight too are this. We have a matrix chat, which is sort of similar to a Slack room. That's kind of like where a lot of our discussion for the project happens. So, but we welcome users with questions at any time. Basically, there's always one of us in there to kind of help or answer questions about anything. Between being across different time zones, it may seem like that. And then we also have a discourse page, which is more of like a type of forum for asking questions as well. So with that, I'll turn it over to Stuart, who's going to talk about search and download with our Fido client.
Now I have to remember how to use Will's Mac. So if I start scrolling the wrong direction, it's because everybody else is wrong. So hopefully you'll have the not instructor version of this notebook open, which is the version I have here, which is fun because I've got to look up the answers. So I know that there are lots of different places to get data from and lots of different ways to get data in Python and in probably every other language under the sun. The SunPy aims to provide a framework which is simultaneously easy to use and very flexible, which anybody who's a software developer knows is an impossible problem to solve. But the SunPy search and download framework supports searching for files to download and also searching for metadata. And it lets you combine queries that hit multiple different data providers into one search, and to look at the results from the search and then decide if you want to download any files associated with those records. Fido is extensible. The core package, the SunPy package, has a list of data providers, which are here. VSO is the Virtual Solar Observatory. It has a lot of different imaging data, as well as some other time series data, but primarily it's a lot of remote sensing data, which is kind of taken by the VSO and has a standardized data model that makes it very easy to search across instruments for different things. JSOC, for those of you who are lucky to have not encountered it before, is where the AIA and HMI data live. If you are using lots of JSOC data, then SunPy can query the JSOC directly, which is a way of being able to get a lot of AIA data in bulk. It's easier to do directly through JSOC than through VSO, but they kind of overlap a lot. And then also there's a bunch of other individual providers where we download data from various archives over HTTP and FTP. And then there's also, as I mentioned, metadata only things like the HEK, which we'll get onto later. So the first off, we've obviously got these imports at the top. This Fido variable that we've imported here is the main interface for search and download. And we will use these attrs that we've aliased to A to save us some typing as a way of specifying what data we're looking for and from where. And as Drew, you're not Drew, as Will mentioned, we use units in lots of places. So Fido is unit aware, where you can specify things like wavelength in any unit you like. So Fido itself knows, is this big enough? Can everybody read this? Should I make it bigger? Fido itself, here we've just imported SunPy, so this is all of the built-in clients from SunPy. We have everything like Cedar Web to VSO and 16 different clients, and you can, in one call to Fido search, you can query many of these at once if you so desire. And as I mentioned, the attrs we've imported allow you to search for different parameters. So the one you might use the most is instrument, and that has a big list of instruments that you can access through all of the different clients in SunPy. And it tells you in this second column here which client in SunPy is that serves that instrument. As you can see, lots of them are the VSO. So let's search for some data. As Will said, we're going to use this CME event in March. So the first thing we're going to do is make two variables, one for the start time and one for the end time, so we can refer to them later. And then the first attr we're going to construct is the time attr. So time takes a start and an end, and then we'll look for data between the start and the end. The instrument attr and some of the other similar attrs support tab completion. So if you do a.instrument. and press tab, you can see a nice list of all of the instruments that you support, and you can pick one. I've already done the exercise, apparently. There we go. Why was that? Whatever. Have a go. Go. Type. Just satisfying my own curiosity now. Oh, we do. Interesting. Okay, so as I said, various other attributes which are like categorical attributes like this also support tab completion. So I was just experimenting with detector there. But what we're going to use is we're going to search for some AIA data. So when you want to construct a Fido query, you can combine attributes together using this Python ampersand operator, which we are interpreting here as a logical AND. So by calling fido.search with this CME time attribute we constructed earlier, and this AIA instrument attribute, we are saying to Fido, I would like you to return me all the records that you can find on any of your data providers which have records between the start time and the end time and with the instrument AIA. And the result object it has returned here is, it's saying it's returned results from one provider. So in this case, that's the VSO, and it's found 174 records. And then it's presented us with this table of results. So the table that it has printed in the notebook here is quite often, it drops some columns to make it a bit easier to read, but the whole table is accessible, and we'll get to it in a minute. So you can look at the full metadata that is returned by whatever client returns you the results. So the stuff we're printing here is the start time, the end time, the source, which in this case is the spacecraft, the instrument, AIA, the wavelength, which is a pair of start and end, so it's a wavelength band. The provider, this data is coming from the JSOC through the VSO. The physical type, intensity, wavelength, wave type, so narrow band observation, the size of the array, the extent, the size in megabytes, that's a lie. And then some extra info that the VSO returns. It should be noted just in general with all of Fido is we just return whatever the data provider tells us. In this case, the VSO returns, sometimes it returns the uncompressed size for these files, but it will ship you them compressed. So the size column can kind of be open to interpretation, I guess. And again, if the VSO has a server gremlin, then it might not return any results when you try it. That happens occasionally, as it does with many providers. So SunPy just returns whatever we're given, basically. Okay, we can extend this query by adding extra specifiers. So if we want to download less data, we can run this query where we're now, as well as asking the time in the instrument like we were before, we're also asking for wavelength. How did that return more? How did that return more results? What? Oh, yes, the size thing isn't a lie. Now, JSOC does weird things. Some of these records are tarbles of many files. Talk to me in the pub later. So in this case, it's returned 900 individual files. As much as I'm sure the people who are looking after HelioCloud would love us to fill up their servers, that's probably going a little bit far. So the next exercise is for you to reduce the number of files in that query. So if you start by copying the query from above, there is a way to modify that query by using this sample attribute, which lets you specify a time range, so it will return one result per time window. So I'd like you to take the query above, add in a sample parameter, and make it so it only returns you one record every 5 minutes. Copy this. Tarbles, man. Tarbles. The instrument thing. That 16? Oh, that's something else.
Sorry.
So I don't know specifically about XRT, but the list of known values isn't necessarily exhaustive. So this table could be incorrect and is probably incorrect. So this list of instruments is something we generate to help out, but the VSO could add an instrument since our last result. All right, that's unlikely to have happened with XRT, but we don't ask a VSO every time we do a query what instruments it supports. We cache them. So there could be many things. The best way to find out whether you can actually get the XRT data is to try and do a search for it if that's the data you're interested in. Okay, hold up your green thing if you've done the search. Two of you, three of you. Okay, good. I'm gonna walk over here and get some water.
There was another question in the chat about when it comes to when we do a search on a time interval, what column is it looking at when it's deciding what time is it looking at when it decides whether something falls in that interval or not?
To some extent, that depends on the data provider. Okay. For the VSO, for instance, I think it is inclusive. The range is inclusive on start and exclusive on end. If I remember correctly, maybe both. No, under some. So the VSO will match any records where the start time is equal to or after the end time, and the end time is before the end time. Right? Did that sentence make any sense? Sure. Each of the Fido clients that gets past the query will pass the attrs and then ask the web service for data matching the values in that attr. So to some extent, the specific like behavior of is client dependent. Whether it like includes the endpoint or not is up to the thing that returns the results, not SunPy itself. I think VSO requires you to have the end time in the table inside your search range, if I remember correctly, but I could be wrong. Okay. Did anybody not manage to write this search with the sample and is thoroughly confused? Okay. Is it misbehaving or are you thoroughly confused? That's a good question. The easiest way is with tab complete. We do source specific ones in a minute, don't we? Okay,
Yep.
I'll come back to this in a second. Some things under here are modules. We'll come back to that in a minute. And then there's a list of attrs here. The classes, these attrs are widely supported by one or more clients in SunPy. Some attrs are client specific. We'll come back to that in a second. So yeah, tab complete. We tried to make, it was a surprising amount of effort and going into a frankly horrifying amount of Python metaprogramming, but we like made these things as tab completable as possible in as many places as we can. So does that? It does that. Yeah, there's also a list in the documentation. Okay. How am I doing? Probably crack on. Okay, so I think I'm gonna give you Mac. Scrolling the wrong way. See, I told you I would. Okay, we have this query here that we've just done in the cell above. What we want to do now is extend the query so that instead of just returning AIA results, we're also going to return results from the EUVI, all of these solar physics instruments sound the damn same, or the EUVI instrument on stereo. And we can do that with, there it is, that's weird American keyboard layout. This OR operator, it's not, is it? It's SECI.
Yeah.
Okay, hang on.
Yep.
There's two ways of doing this because, no, it's all lowercase.
Ju-
Right, I've messed this up, haven't I?
Yep, just, yeah.
So it's now also way too long. So I'm going to put some line breaks in so that we can, this is an egregious breach of PEP 8, by the way, but we won't complain too much. So as we've been using already this ampersand operator for logical and, so we're asking for time and like records that match this time and this wavelength and this. This is a bad way of, I'm going to change my mind on how I'm going to show this to you. So, right, start again. So we've been using this AND operator for like, you know, restricting based on multiple things. But what we can do is we can use this OR operator for things which are, we'd like, you know, records that match either one of these. So just for clarification, SECI is an instrument suite and EUVI is a detector inside SECI. We won't get into the slightly confusing behavior of VSO right now, but for the moment, I'm going to use this one. It works both ways. They made it easy for people, but also confusing at the same time. So doing this with the bar operator, pipe operator, or whatever you want to call it, is a logical OR. So if we use this inside a query, we'll get things that match either one of the instruments. Hopefully that's not too complicated. So we can make this into a little intermediate variable, and then it will hopefully make this a little bit easier to understand. So I can't type. No, wait, it's not old habits. It's probably good that I'm using a foreign keyboard. It slows me down. I say that, but my laptop keyboard is also ISO layout, but never mind. Okay, so this is the same as this. Now we have results from, we have two separate providers returning results, which is a little bit misleading because really it's just the VSO twice. Under the hood, it's made two separate queries to the VSO here, one for AIA, one for SECI. And we've got 36 results for the AIA table, the same as we had before, and we've got 33 results for the SECI EUVI table. Why does that stay formatted different? Such questions. Right, this is the same query. That's right. Okay, you literally did just run that, right?
Yeah.
Okay. So we can continue this pattern of using intermediate variables to build up significantly or progressively more and more complicated satellites. So we're going to combine all of that query we just did, apart from the time, into a variable named AIA or SECI. So we're going to look for AIA or SECI data at 304 angstroms, or more correctly, 30.4 nanometers, and every 5 minutes. And then we're also now going to ask for GOES time series data for the X-ray luminescence of the sun, or whatever GOES does. I don't know. I'm no longer a solar physicist. And we're going to combine these things together. So we're going to say we want all data for the time range we're interested in for AAA or SECI or GOES. And that should give us 3 results. There we go. Results from 3 providers, 36 images from AIA, 33 images, and also 1 day-long time series result from XRS. Okay. Now for EUI. So EUI on Solar Orbiter is slowly being indexed by the VSO, but they haven't caught up with this event we're interested in. And SunPy provides one of the affiliated packages we have. I guess it's not actually technically an affiliated package. There is a package called SunPy SOAR, which provides a plugin for Fido that directly queries the SOAR archive for Solar Orbiter here at ESAC. And by importing this package with SunPy SOAR here, we will have registered that client with Fido. So now you can see we have this SOAR client at the end of the list of clients supported by Fido, and we can now search that archive. So we're going to build up this query. We're going to search for this specific data product. As I mentioned earlier, this is a client-specific attribute. So now that we have imported SOAR, you can do a.SOAR to get attributes specific to SOAR, and that namespace needs clearing up. That's the second issue I found I need to open in just this notebook. Happens every time. And you can ask for things. Yeah, is it just product?
It's just product.
It's just product.
Yeah.
Oh, and identifier. Maybe.
No, those,
Anyway.
it's just product.
So by including this product, this a.SOAR.product, you're only ever going to get results off of the SOAR client.
Hey, Stuart.
Yeah.
Someone said in the chat, I'm curious, is there any reason for sending the attributes like that and not as args or orgs?
Not as what, sorry?
Args or KW args.
No, that's a good point. All of this, blame incorrect keyboard layouts. This and are functionally identical to each other. If things don't exist in the tables and aren't available in tab completion, you can just pass them in as args to the attribute instead. Just doing it this way, it aids discoverability because you can mash tab at various times and see if your instrument is there. Well, that's the idea anyway. So now we're going to combine all of these queries for all 4 of our instruments together into one query. We're going to search for the time with AIA or SECI or GOES or this EIA FSI 304 image product. Now we should have 4 tables in our results. We have the AIA, the stereo, XRS, and also now 18 level 2 images from the SOAR archive. And now we're going to download them. So once you've got a search result object that you're interested in, you can download it with fetch. Fido is not an acronym, but it is a very bad dog pun. So this is now going to download 88 files from the VSO, wherever our XRS data comes from, which is direct from NOAA, right? So it's going to make requests. It's timing out. VSO is broken. Hey, Jack, I know you're on the call. Fix it. Yes.
Sort of related unrelated question with this. So you know, fetch sometimes break, but if you already have data, say somewhere, and you're very lazy, like you don't plug in like a data sort of thing, it still checks. It still makes those queries checking.
Yeah. So the way that this ends up working. This varies a bit client to client, but the way to assume, like, it only knows the file name it's going to download at the last possible minute. So if a file with that name already exists, it will skip the download unless you specify overwrite is true. But to get to the point where it knows the file name to compare whether it's there or not, you have to do the search, and then it has to go to the data provider inside fetch and go, I'd like this record, the file for this record. And then the data provider comes back and goes, here's a URL that gets you that record. And then we go to that URL and it tells you what the file name is going to be. And then it goes, oh no, that one already exists, and skips it.
Stuart, while you're waiting for this data to download or not download, there's a question in the chat of why use this adder system at all, and instead of just passing args or quargs to Fido.search.
The idea of the ATAS system, which is one of the few pieces of SunPy that existed before I joined the project, but is to allow you to construct really complicated queries like this. If you were just passing in instrument as a keyword argument, it could only have one value, and then there wouldn't be as clear a way to specify I want this instrument or that instrument. And the idea of combining the search together, building the search blocks up in those logical attributes, is that it lets you construct complicated queries that hit multiple different instruments at once, which you could maybe argue you just make 4 calls to Fido.search, but where's the fun in that? Yeah, so what's happening here is the VSO have had some issues with one of their SDO servers, and the first 5 or whatever files it's trying to download, the request to download the files is timing out. So given some amount of time before this times out, it will eventually download everything but the AIA data, because SDO7 is going to time out. So part 5 is just sitting there waiting.
It's okay, because we anticipated this. It's all right.
It's a shame, because you don't get to see my lovely progress bar. They're so pretty. You can.
Do you want to explain what the path equals?
Oh,
yes.
yes. Yes. Okay, so you might have noticed here, I'm going to have to kill this so that I can continue doing stuff. We've specified a path here. This is local to the current directory, right? Or
yep.
inside, yeah.
Yep.
So we're going to download the files into a directory named data next to wherever this notebook is being run. And then it's going to make a directory called instrument, not called instrument, but with the name of the instrument. You can see the list of things that you can put into the path for a given query by doing, I can't remember what it is. There we go, path format keys. Oops, that's a method. So the queries, the things that you can put in these curly braces in the path for this specific query are end time, start time, and instrument, because they're the only columns that all of the data has in common. But what it's going to do is it's going to make one folder for AIA, one folder for SECI, and one folder for EUI, and presumably one folder for XRF, which can be useful to just not have a directory with thousands and thousands of files locally on your machine. Okay. I go all the way up here and delete this.
Some people say that theirs is downloading, so it's
Sure, good.
working for someone.
We're probably DDoSing the VSO. If I make this query again, but without AIA, just to show that it actually downloads. Nobody needs AIA data. Satellite's gonna die soon anyway. We all need to get used to not using it. Okay. Speaking ill of SDO is heresy, by the way. So this is, it downloads a given number of files in parallel. And the library that renders this progress bar has a bug where it takes ages to clear the completed results, but I would complain to the maintainer. Who's me? If files fail to download or, all right, and the result is a results object which looks an awful lot like a list of file paths. So this is now a list of paths to all of the files that it's downloaded. If any files fail to download, you can just pass the files object back to fetch and it will try and re-download any failed downloads. But there weren't any, that's fine. We don't need to download the AA data, Will, right? You can.
Yeah, it's fine.
Cool.
There's a contingency plan.
How long do we have before the break?
30 minutes.
Sweet.
Yeah, that's good.
You can do math in 30 minutes, right?
We'll get through what we get
Doubt.
through.
Okay,
All right.
you can listen to Will again now. Yeah. So the question was, is there documentation for building plugins? There is inside the SunPy documentation under the developer guide. There's a whole page on building a new plugin. I'll pop the link in the chat.
Yeah, more external Fido clients would be great. I think the SOAR client is one of the few external ones. And radio, there's one for.
There's some in Radio Spectra. There's one in the DKIST package, but there's no data for you to download with it yet, unless you know the secret URLs.
Hey, Will.
Yes.
Question. Maybe I missed it, but does Fido allow to get users to get in situ data? I don't see any listed on sunpy.net.adders.inst.
Yeah, most of the in situ data is available through the Fido web client. And then also, as well as through the SunPy SOAR client. So yes. Any other questions before we move on to the second part?
I don't know whether Cedar Web, no, Cedar Web does register atters. I don't know. It's possible that the list of instruments is incomplete and doesn't include everything that's in Cedar Web. I can't remember.
Let's do a quick test. This might be a mistake. Nope. There is a list of data sets available from Cedar Web, but yes, unclear.
Oh, are they not instruments? Scroll up. Yeah. So just query Cedar Web, you use dataset instead of instrument, which is why they're not in the instruments list.
There you go. Okay. Any more? Are there any more in the chat related to Fido before we move on? Okay. All right. So if you recall the slide from the beginning of this, well, I'll just flip back to it. No need to recall it. So this covered data download through Fido using different disparate clients with mild success, and nominally downloaded some data. And now we're going to talk about data containers. So once you have searched for the data that you want, you've downloaded it, what do you do with it? How do you load it in using SunPy? So if you'll recall from Stuart's presentation, we got AIA data, we got stereo data, EY data, and then time series data from GOES, the GOES XRS instrument. And so now what we're going to do is show how we load all those things in. So I'm doing a bunch of imports up here that I'm not necessarily going to walk through, but the important ones are these two modules, SunPy map and SunPy time series, which are the ones that provide these data structures for these two types of data. So one modification that we're going to have to make on the fly because of these download issues that we're having. So you'll see that here in data is, so if your download succeeded, there will be a data folder inside your SunPy tutorial directory. And as Stuart said, we use that data / instrument with the curly braces. And what that did is it created a separate directory for each one of our instruments that we downloaded. And then the fits files for those queries are located in each of those directories. Because of the problem with the AIA downloaded, there's not one in there, but it's okay because we put all of this data on this shared folder already. So if you go back all the way to home and look under shared and look under SunPy and then data, we have AIA, EUI, SECI, which is the stereo A data, and then XRS. And we won't worry about this last file for now. So we're going to modify these paths here to, we can just go back 2 steps, I believe, to shared, SunPy, and then data. So if you're, so what? Yes, yes, yeah, they all did. So for if your data didn't download, it's okay. The data is still there. You just need to modify this one path here to be prepended by this shared, the two dots / 2 dots shared SunPy. Yeah. So we'll just do it for all of them so that you can see what this looks like if your download didn't succeed, which is okay. All right. So what we're doing here is we're just grabbing a list of all the files for AIA, for stereo, and for the UI, for the solar orbiter. And now what we're going to do is we're going to create a map object for one file from each of these. So I'm just taking one, we download a series in time. I'm just taking one snapshot in time to illustrate what's going on here for each of these instruments. So I'm creating 3 maps. To create a map, all I need to do is pass the name of this file. So if I go and look at this AIA files, this is just a list of these fits files in the shared directory. I go and index one of them, and if I do it correctly, I'm just getting back one path. So all I'm doing is passing the name of the fits file to sunpy.map.map. And so what you can see here, and so this what it says is it creates a map object for this specific data type. And one of the nice things about map that was added a few years ago is that we have this nice little preview function that inside a notebook, all I have to do is just put the name of the map, and I get back this nice summary of the metadata. So I can see, this comes from stereo. It gives me the name of the detector, what wavelength it was taken, when it was taken, the exposure time, all these useful things. It also gives me a little image preview with the helio projective coordinates. So like Brett showed earlier with the sample data that he was showing. I can also flop back just by clicking on it between the kind of physical coordinates and then the pixel coordinates. And it's often, depending on what your application is, it's useful to work in one or the other. And then this plot down here just shows the distribution of intensities. And if I click on this, I can flop between a PDF and a CDF of those pixel values. There's another, in addition to this quick look functionality, map also provides a plot method. And we're going to talk a lot more about this later. But what this provides is a more, this is what Brett was alluding to in his tutorial about SunPy providing kind of easier to use, but more specific wrappers around this whole idea of creating an axis with a projection based on the WCS and calling imshow. All this stuff is kind of wrapped up in this plot method. And so you can see what we get back is a plot of the sun with the name of the instrument, the date, labels on the axes. And what we'll do later is show how we would customize that to make some sort of more, say, publication ready plot. Okay, is everyone good with that? Loading data, image data into a map? Okay, great. All right, so now what is this map thing? What does it provide us? So one of the main advantages that we have these data from these 3 different instruments. By loading it into the map, we're sort of homogenizing the data, and it gives us a unified interface to these data products from these different instruments. So, and it gives us, exposes this metadata in various ways. So fundamentally, map just provides the data, the image data, plus the metadata, right? And we can access those 2 components by doing, so this is just in the case of the AIA map. We can do this .data attribute. We can see, this is an array, a NumPy array, and we can see it's integer type. We can also look at the metadata using this .meta attribute. And what this provides is essentially a dictionary of the fits keywords that were inside of this this fits file that we loaded in.
Will, people are having trouble loading the data from the shared folder. Can you go back to the top and
Yes.
get the pathway?
Yes. So you will need to modify your path. So originally it just said this. What we want to add is we want to go back down 2 levels to shared, to SunPy, and then to data.
Is anybody in the room struggling? Need a hand? Maybe we'll figure it out.
Yeah, if there's issues, yeah, please. Yeah, I think everyone should have read access to the shared data folder. I don't think that should be an issue. Does anyone else have any other questions while we're waiting a little bit? If you've loaded the map, are you able to generate the quick look plot in the notebook? Look okay? All right. So just to emphasize again, this is just a NumPy array that we get back, so we can do things, any usual operations that you do on a NumPy array, right? We can look at the shape, dtype. You can index it in the ways that you would a usual NumPy array. Similarly, we can, you can look at and you can grab the keys straight out of this metadata dictionary as well. That makes sense. Okay, so in addition to exposing the raw metadata to you, which is often not terribly useful for us as scientific users, map also creates these higher level derived properties from the underlying raw metadata. So these include things like the wavelength for our observations. So remember in that last notebook, we were looking for 304 observations from all 3 instruments. And notably, this returns the wavelength as an AstroPy quantity. So if I look at oh, of course, why is this doing this to me? If I looked at the type of this, it's a quantity, so it has units and value attached. And this is true for we strive everywhere across the SunPy package for all of if our inputs are physically meaningful, they have to have units attached. And similarly for our outputs, if they're outputting a physical quantity, then they have units attached. So you can see similarly for, this is the radius of the sun in meters for this as derived from the metadata of this particular map, as well as the angular, the measured angular width for this instrument. And notably, you can see for UI, this is much larger because, oh wait, does that make sense? It is much closer. Yes, yes. And this is, again, its output as a quantity, this time in arc seconds. We can also look at useful things more related to the data itself, like the processing level. So we can see that this is level 2 data from EUI, or looking at metadata like what instrument is this from. So you can see if we look at the stereo map, this is from the SECI instrument suite. Then notably, we also expose the unit that the image data is taken in for each of these. So you'll see in this case, for the UI data, is actually taken in counts per second. Interestingly, if we look at the AIA data, if we look at the unit for this is in counts, and we'll come back to this a bit later. But the fact that these two things are in different units. Okay. So like I mentioned, we're also going to do a coordinates demo. That's kind of the next section, but just a brief aside on the coordinate specific information that map exposes, or attributes that map exposes. So in particular, it drives information related to what coordinate system this image was taken in. So Brett mentioned earlier that the image of the sun that he was demoing with was in a helioprojective coordinate system. And for each of these helioprojective coordinate systems, they are defined by an observer at a particular location. And Stuart is going to touch on this a bit more in the next notebook as well. But we can get information related to what coordinate frame these are taken in. So you'll notice if I look at the coordinate frame attribute on this AIA map, it's in a helioprojective frame. But then you also see that this observer is a heliographic Stonyhurst, is in a heliographic Stonyhurst coordinate system. And what that's telling us is the position of the observer that defines this particular coordinate frame. And we can look at this more directly by looking at this other derived property called the observer coordinate. And which again is, it's exposing this exact same property that's listed in the coordinate frame here. And these are derived from the metadata in the map itself. So it's looking at the FITS keys and it's constructing this sky chord object that we heard about before that defines what our coordinate frame is. And we can do this for each one of these different maps. And what this is telling us is the position of our satellite. So our coordinate frame is defined by our observer position, which in this case is just where the satellite is located in this heliographic Stonyhurst system, which is more or less a fancy name for a spherical coordinate system with a particular origin defined by the position of the Earth. So we can plot these positions using these derived metadata attributes on our map. And what we get back is something similar to that plot that I showed from the solar mock tool earlier. So I apologize, let's make, we can make these markers a bit bigger. I don't know why I made them so small. That did not help. Why did that might be too big, but here, you can see them now. So that's right, yeah. These are not to scale, make that very clear. So we can see the STO is right on the, or more or less on the Sun-Earth line here. stereo A is offset by, what is this, nearly probably about 30 degrees here. And then UI is offset by 90 degrees the other way, and then much, much closer to the sun. And again, this is similar to this initial plot that we saw from the solar mock tool. And we can use, the point here being that we can use the attributes is derived from the map of our observer to look at the relative locations of these spacecraft from the metadata of these images.
It's also, yeah, it's worth just pointing out that the difference between the solar map plot and that plot is that it's reading it from the files and not like kernels or like orbit calculations and stuff.
Right. Yeah. Yeah. So I believe so. And again, there will be a solar mock tutorial in a few days, so you'll hear in much more detail about it. It does use, I believe, the SunPy coordinates infrastructure, but right where it queries the data from is not from a file. Yeah, that's a really good point. Okay, are there any questions before we move on? Thoroughly confused by now. Okay. Yes. Yeah, so the question was, how does map know the mapping between the instrument keyword and that particular attribute that it's exposing to you? Did I get that right? So yeah, what's happening underneath is that we have a bunch of source specific code for reading in FITS files from different sources. Now, generally speaking, these files follow the FITS standard, and so there's a specific key for like wavelength, for example. There's a specific key FITS key that denotes wavelength, so we can pull that out of the map. And there's a specific key for denoting the wave unit. We pull those two out, we smash them together, make a quantity. That's your wavelength attribute. There are cases where there are deviations from the FITS standard or just differences between data providers. And what we have source specific code in the map subpackage in SunPy to deal with those inconsistencies. So for example, there's an AI, well, here, I can just show this. So if you look at the actual type of AIA, it's an AIA map. If you look at the type of, let's see, MUI, it is an EUI map. In practice, as the user, you shouldn't have to worry about that because it's just a map. It should expose the same attributes, but this is just to show that there's some source-specific parsing code to deal with those inconsistencies between keywords. Yeah. But what we strive for is sort of the same interface to all 2D imaging data. Yeah. Okay. All right. Let's make some nicer pictures than we showed above. So, one of the nice things that map provides, like I said in the beginning, is this plot method. And at a minimum, so we can just call this plot method, and you'll see in this case for an AAA map, this isn't giving us back a particularly useful image, right? The color bar is set such that it's hard to see the sun. Maybe we want it to be a bit bigger. Maybe we want a different normalization. Maybe we want a color bar. And so the point being is that this provides a kind of sometimes a decent first look. But what we can also do is use this plot method. We can customize this plot method using matplotlib and also some functionality provided by AstroPy for creating projections on our map based on the WCS. So at a minimum, you know, we can make this plot a little bit bigger. We can set the maximum and minimum limits on the color bar. And then we can also draw a grid on top of the map. In particular, a heliographic Stonyhurst grid, which again is this spherical coordinate system. So you can see here, okay, this is already starting to look a bit better, right? We can also do things, you know, basic things like adding titles. We can add some axis labels, so we can sort of build up complexity in our plots. Here, what you'll notice is I'm creating a projection and based on the map itself. And I believe when Brett did this, he used the WCS keyword explicitly. You can also just pass map in and it will know to create the projection from the WCS information attached to the map. I'll just go ahead and create this map here. So you can see the color bar looking a bit better. We've added the color bar scale here, and we've also set some. Let's make this also a bit bigger. I don't know why it's so small. We've added some labels, HPC lat and HPC lon. Maybe we didn't like the default labels that it's giving us, and then we set a title here. But the point here being that even though map.plot on its own might not give you the best looking visualization out of the box, we try to have sensible defaults for things like the color map or the normalization of the color bar, but you can also customize all of these things. I will note also that you'll notice that the color map is not like the default, matplotlib color map, which I think is Viridis, or the grayscale one, right? We're actually choosing, SunPy will actually choose a color map, or the map subpackage will choose a color map based on the instrument specific source. So in this case, we've chosen a color map that's commonly used for the 304 channel of SDO AIA. So we also look at using a different normalization. So if instead we wanted to use a log stretch plot to look at our UI map, we can do that just by using this image normalize functionality that's provided by the AstroPy visualization package. And we can use this stretch keyword to say we want to stretch our color bar using a log scale rather than the default linear scaling. You can see this kind of brings out our kind of CME bubble structure here that we're seeing right off the Eastland. So you'll notice in the notebook that I believe the answer to this exercise, if you will, was left in there. But the exercise is basically, okay, if I have this map, how maybe I don't like this default color map that SunPy is choosing for me. How do I change that? So I presume everyone was able to do it since it's already in the notebook. But it's also relatively simple. I can just use this CMap equals keyword and say I think the example that I used in there was Inferno, just one of the matplotlib ones. I have a different color map. So lastly, there's an example down here that there's a lot of this last block in this section is a lot of, I realize it's a lot of code. It's not necessarily important to understand, in this session what each one does, but this is just to show that you can build up, you can add pieces, still using this plot functionality where you get these nice projections on your axes based on the WCS information to build up these much more complex plots.
Hey, Will,
Yes.
we're actually right at the break right now.
Perfect. I'm at the end of this section, so that's great timing. So I'll just make this and we can So that what I'm just showing here is a subplot of all three of these sources with some nice labels. Yes, is there another question in the back?
Hi, is this on? I was wondering how you came up with the Vmin and Vmax for the plot to change the scale.
Manually. I mean, I looked at it and I just kind of adjusted it to see what looked best. What's often, if you, of course, you don't want to always do that. What's often useful, and I guess I didn't emphasize that very well, is to use this clip interval functionality, which will automatically clip to, like, if you have one outlier. Sometimes if you have a really, let's say if you have a really like hot pixel, it's really bright, it's like an order of magnitude greater than everything else in your map, the normalization will be thrown off and you'll get like a max. It's like way bigger than the, most of the data in your map. If you use this clip interval key to clip to like some percentage of your data, it will automatically choose that Vmin and Vmax based on that percentile range, if that makes sense.
I guess so. So the Vmin and Vmax that you've got in there can be found automatically.
Yes, yeah, using the clip interval functionality, yeah. Or
using that.
if you want to just choose them, like I chose the Vmin, I put the Vmin and Vmax example in there just to show that you can do that manually, and that's what I did. I just chose a sensible range that gave me a map that was kind of fit to basically the dynamic range of the map itself. You know? Underneath the hood, I believe this clip interval used the asymmetric percentile interval. There's a function in the AstroPy visualization package that's called.
A manual example of using min-max interval and the stretch and things in notebook earlier.
Yeah, so there's all of that is I guess it's in the earlier AstroPy tutorial, but what our clip interval functionality is, again, just a kind of a convenience wrapper around that. Yeah. I will go ahead and end there so that we can take a break, so that we're still roughly on schedule, plus or minus a few minutes. There is an exercise down here, but it's not really an exercise. It's just a question for you to think about during the break. We can talk about it when we come back. And I can also roam around and answer questions. Stuart and I both can during the break. So I'll go ahead and stop there, let everyone take a breather. Okay. I think we're gonna go ahead and try to finish out for the second half of the SunPy tutorial. So so I left you with this nice plot and the relatively complicated code that produced it. And with this question of, you can see that the grid lines on each of these that we've overlaid for the helioprojective grid, the solar orbiter one in particular, the UI map, is tilted relative to the others. And the reason for that is that this is due to the roll angle of the instrument itself relative to solar north. And you can examine that by looking at the this rotation matrix property, which basically tells you it's the rotation matrix between your pixel axes and your world axes. So in the case where the two were aligned, this would be a diagonal matrix. So I'd have just ones on the diagonal, zeros everywhere else. But you see we have off diagonal elements, which tells us that there's some misalignment between those two. But that's okay because our map knows about this and it can construct a plot, or the WCS knows about this, and we can use the WCS to construct the plot appropriately. All right, so we're gonna move on to, we're gonna cruise through animations quickly. So there's, I won't spend too much time on this, but there's also this thing called map sequence, which is basically just a container for holding a bunch of maps together. And in particular, it's often useful when you have a bunch of maps at sequential time steps, like we do in this case. Really, the only thing we're gonna look at here is the fact that we can use this map sequence. So again, sort of each individual component of this map sequence is just a map, but we can use this map sequence to create a visual, an animation. And so what we're going to do first is just create a normalization that is appropriate for every slice of our animation. And we're not going to worry too much about what that is, but we can use this time the plot method on our map sequence is giving us back. So it's showing just the first frame. It will show just the first frame of the animation. But what this UI underscore ANI or Annie is an animation, and we can, or it's a matplotlib animation, and using some HTML/JavaScript magic, we can display this in the notebook after a little bit, and it will give us back an animation of our CME that we can now play here. So we can see this thing going off on the west limb here from the perspective of a UI. This little animation thing is a matplotlib animation, so you can also save this if you wanted to, like an MP4, or there's lots of different ways to output this animation, but this is just for display purposes. We're just sticking it straight in here in the notebook. Okay, pause that. Similarly, we can also do this with stereo, because we have this stack of stereo images as well. We can make, okay, we won't worry too much about these warnings that are going off. I can talk about these later if people have questions about this. But we can also animate what the CME would look like from the perspective of the stereo satellite. So we can see the eruption going off right here, but because of the relative angle between solar orbiter, right, and the stereo spacecraft, recall from our plots of the spacecraft position before, we're seeing this, almost not a little bit off from, face on from the stereo point of view, and then we're seeing it, side on from the solar orbiter point of view. Okay. So moving on. So are there any questions, any quick questions before? Yes. Right. Perfect. Great. So yeah. So what I would do is, yes, Sandy's suggestion of restarting the kernel, and then it's okay. Do not run. I'm sorry that you cannot produce this nice animation. You can watch mine, but do not run this like from here down. Just skip that. Sorry. Yeah, probably the reason because it's probably stacking. Oh, so no, this is what it is doing. It's stacking every single array in our sequence of images into one big matrix, and then using that to get the limits for the normalization. And it's probably just that array is overwhelming the memory of your kernel and it's killing it. But that's okay for the rest of the notebook. Sorry that you don't get the nice movie. You can watch it more. I'll play it again. I'll play it again so we can see it up here. It's yes, Sandy. Okay.
Yeah, for the animation, does the pixel to world chords mapping change from frame to frame? Each transform is in each image, I suppose, question.
Yes, all right. I'm not.
Yes,
Stuart's on top.
the short answer is yes.
Yes, it does. The reason is slightly more complicated. Okay, so now we're going to talk about, Brett touched on WCS. We're not going to say a whole bunch more about it, just to say that map exposes the WCS information as well on this with this WCS attribute. You can see that it's just an AstroPy WCS object. Again, we're using AstroPy underneath the hood wherever we can because it's great. You can do, this was already demonstrated, but you can do things like pixel to world. If I want to know what is the coordinate that corresponds to the bottom left pixel of my map, I can do this just putting in 0, 0, and it returns to me the sky chord here. We also have these attributes, these handy attributes that tell you that give you the bottom left coordinate and also the top right coordinate as well, though I haven't shown that here. And so if you do something like pass the bottom left coordinate into your world to pixel, you can see that I'm basically getting back 0, 0. I mean, this is 10 to the minus 10, 10 to the minus 12.
I mean, all the bottom left did was pass 0 into pixel to world, so it's just going
just round tripping.
Yeah.
Yes, exactly. Yes. So you can also see that the center. We can also confirm that the center coordinate falls on the center of our map in pixel space. We can look at if I pass this through world to pixel, I get out my dimension -1 divided by 2. Yes, which I can confirm here. Great. Okay. Importantly, for the example of AIA, you'll notice that if I construct a coordinate that's at the center of the sun, so it's 0, 0, right? And our helioprojective coordinate system, 0, 0 is by definition the center of the sun. If I pass this through to world pixel, this is not the center of my map. And that's because there's an off point between the center of the image and the center of the sun in an AIA image. But that's okay. So we can always correct for that, but it's okay because our coordinate system knows about this. So we can still do all these transformations, still work despite that, because it's encoded in the WCS information. In the interest of time, I'm going to leave this exercise for homework. I'm happy to talk.
You will be examined in the morning.
Happy to answer questions at any point during the week. I'll be here all week, and so will Stuart. So we can talk about this at any time. So I'm just going to quickly talk about some basic methods that we provide for manipulating image data as well. So the two that we're going to touch on are rotate, which, as you might suspect, rotates your map, and then submap, which is for doing cutouts. So if I call this rotate method does a rotation within the image plane. So you can imagine an axis coming out of the page to you, and I rotate. I'm doing a rotation about that axis out of the page for my image. By default, what rotate will do if we don't pass it any arguments, which may seem a bit strange, I'm not passing any arguments. What it will do is that it will correct for that roll angle that we saw earlier in when we were looking at the orientation of our grid lines on our image, right? So it knows what that relative orientation is of the pixel axes relative to the world axes, and it will rotate such that those two are aligned, right? So you think of it as it diagonalizes the rotation matrix. Is what it's doing. So when I do this with the stereo image, it's not terribly. It doesn't look all that different, right? I should have done this with the UI data.
No time for that.
But yes, but if I again look at my relative rotation matrices that you can see in before rotation, I have these off diagonal non-zero elements. After rotation, I have ones along the diagonal, basically zeros off the diagonal. Of course, I can also feed in some rotation angle to rotate this by. So here I'm going to rotate my stereo image by 30 degrees, and importantly, this is not 30 degrees relative to 0, it's 30 degrees relative to the current rotation of the image. Now I get my rotated image back. There is I have an exercise here that's, again, we'll leave that there, but it's basically just saying, okay, if I wanted my orientation between my world axes and my pixel axes to be exactly 45 degrees, how would I do that? So feel free to work on that, but I'm gonna move on. So again, we can also apply this rotation to our AIA map in exactly the same way. We don't provide any arguments, and it will just align those the pixel and the world axes. Any quick questions before go on about rotate? Does that all make sense? Yes. Wow, what a great question. We will show exactly that.
Assuming we don't run out of time.
The next notebook. Oh, sorry. Yes. So yes, sorry about that. So the question was, can we do a reprojection of a full disk image into a heliographic projection? And the answer is yes. And we're going to show that in the next notebook, exactly how to do that. So yes. Okay. So the next, one of the most common. Okay, I'm going to say this in words. You could do submap using this submap method. You basically give it the corners of the cutout that you want to do, and it returns you a cropped map. And so you can specify this in terms of your sky coordinates or in terms of pixel coordinates. They work both the same way, and there's also an exercise that you can go through here. Okay, so that's map. I realized the end of that was a little rushed. Again, I'm happy to answer questions at any other time. And then Stuart will also touch on some intricacies of map in the next notebook. So the other data structure that we're going to talk about is time series. This is going to be much more simple than what we just went through. If you're running this notebook again, you're going to adjust the path here, which I'm
You can just use / on shared.
Oh, I also downloaded the data already, so it doesn't matter. But yes, so it's in shared. If you haven't downloaded the data, just append that same shared thing that we did in the beginning of the notebook to adjust the location of where this is. So what I'm doing is grabbing the GOES data, the GOES XRS data, which is, it just basically does a full sun integrated time series into I think it's a hard X-ray and a soft X-ray channel. It's often used, what is most commonly used for, setting like what the classification is for a flare, depending on the peak flux in each of these channels. So I can create a time series from these, I believe it's a netcdf file. And I can access, again, similar things like as we did for map. I can access the metadata. I can see, we have a intensity from the A channel, from the B channel. It gives me what time these were taken over, various other bits of metadata. Just printing it to the notebook gives me this nice little preview similar to map. I can also export, so these are time series objects, but I can also easily export these to AstroPy tables, which we heard a lot about earlier, or to pandas data frames. If these are the things you're more comfortable working with, then you can export them to either of these types of data structures. There's also various things you can do, like looking at what columns these belong to, what the observatory is. Again, it's GOES 17 specifically, and then what the units are. There are also various ways to look at a particular time interval. So this GOES returns 1 file per day. We don't really care about most of the day. We care about the stuff around the time that the CME went off. So we're going to truncate around those times. And I'm grabbing the time from my first EUI image and from the last EUI image. And I'm using those as my bounds for the truncation of my time series. You notice when I return this, that I get this nice flare that's happening right around the time that my CME is going off, coincident with the launch of the CME. And I'm just providing another example of how to plot here. Okay. I realized that was a whirlwind tour of both map and time series. If people have questions, again, especially on those exercises, I'm happy to go through them like any day this week, but I'll turn it over to Stuart, who's going to look at do our last notebook on coordinates and reprojection, more excitingly, to wrap everything up.
Just gotta try and get pretty pictures in these things. So this notebook is going to go through some SunPy coordinate stuff and into Reproject, as Will mentioned. The Reproject is an AstroPy affiliated package, which because SunPy extends the AstroPy coordinate infrastructure, sky coord and stuff that Brett showed earlier, Reproject just works with SunPy data because Reproject uses the AstroPy coordinate graph. And as long as you've imported SunPy coordinates, Reproject suddenly understands solar physics coordinate systems, which is the power of this interoperability. So we're using a few packages in this, as I said, Reproject, but also AIA-Py to do some calibration on the AIA data we downloaded earlier, or not, as the case may be. So I think Brett showed a kind of version of this graph earlier, but this is a bit more SunPy focused. So SunPy.coordinates, as has already been mentioned, extends AstroPy coordinates. We got involved with writing AstroPy coordinates from the beginning and made sure that they work together really well. And once I finally managed to nerd snipe Albert, he linked the two together. So we have ICRS and various other astronomy related frames implemented in AstroPy, and through the transform graph, you can convert from heliographic Stonyhurst and other solar system coordinates and sun-based coordinates into AstroPy and back. So if you ever really wanted to overplot galactic coordinate contour lines on your solar data, you could do it. Especially now that there's that assumed spherical screen thing. Okay. there's a lot. I appreciate I don't have a massive amount of time to crack through this, so I'm not going to go into too much detail, but we've mentioned it a bit already, but it's probably worth just taking a couple of minutes to talk about the solar frames a little bit more. Those who aren't particularly familiar with solar imaging data, there are two main types of frames in general, but in specifically going to talk about the solar versions, which are frames that have the observer as the origin. So when you float around in space or stand on the ground and stare upwards, you can describe the sky as the inside of a sphere. You can like measure an angle up and an angle round and a distance. And that's coordinate system is centered on you as the observer at the origin. So imaging data generally has a coordinate system which is centered on the camera that took the picture. Those kind of coordinates are like the helioprojective coordinates that we have discussed already. The other kind is where your observer is at different locations. Quite commonly in Astro, the ICRS reference frame uses the Barry Center, if I remember correctly, and but quite commonly for solar work, we use the center of the sun, and just the heliographic Stonyhurst coordinate system is very equivalent to Earth's longitude and latitude coordinate system, where you have a North Pole and a prime meridian, and you have latitude and longitude centered on the center of the sun. The only complication of that is you have to define your prime meridian, which in heliographic Stonyhurst is defined to be the line of longitude that intercepts the Sun-Earth line. So as the Earth goes around the sun, the prime meridian moves with it. And the X and Y axes are perpendicular to those and through the North Pole of the sun. So let's go through creating some of these coordinate objects. I guess, does anybody have questions on specific coordinate system things before we get into the code? Yes. Some of them are effectively equivalent to other ones. I can't remember. There's a full list in the SunPy docs. Maybe we'll find it and link it to you in the chat or something. I didn't, yeah. Was it, what did you say? GESEQ? The question was whether the GESQ coordinate system is implemented, and I'm not sure without checking, but I want to say maybe not, but it could be one of the ones which is just a different name. I get confused. People are bad at naming things. Lots of coordinate systems have many names. Right, so here we have constructed a heliographic Stonyhurst coordinate frame. The coordinate frame here doesn't have a coordinate position in it. It's just the frame in which you could measure coordinate. As I mentioned, because the prime meridian of that coordinate system follows the Earth, you have to specify a time for which your coordinate frame is valid. And that time is used to know the location of the Earth at that point in its orbit, and that defines your prime meridian. You only technically need that piece of information if you want to transform that coordinate system into another coordinate system that doesn't use the Earth as a reference frame. You can define coordinates which are isolated. You can do this with helioprojective as well if you don't know the obs time or whatever. You can define self-consistent coordinates, but then you can't transform them unless you have the relevant metadata. So here we're constructing the coordinate frame with the metadata. It also has the radius of the sun. It uses the radius of the sun as the default distance coordinate for the spherical coordinate system if you don't specify one. And also some other things, if I remember correctly. So here we're taking that frame that we've defined at that given time, and we're specifying a coordinate point, in this case, just a single coordinate point in that reference frame. So we're saying 10 degrees longitude, 20 degrees latitude, and 1 AU from the center of the sun. So, and then we're specifying the frame that we just created. So that is constructing a sky coord object that describes a single point, 1 AU away from the sun, 10 degrees, oh goodness, which way round is it? That way, to the Earth, and 20 degrees above the solar equator in latitude. You can print these things using standard Python string interpolation. You can also, as Brett mentioned in his session earlier, one of the parts of the AstroPy coordinate stack is representations. When we specified it above, we used a spherical representation, latitude, longitude, and distance. But with using this representation type argument, you can also get it to specify in Cartesian components. So it's this point in 3D space is 0.9 AU by 1.6 AU by 3 AU away from the center of the sun. Whichever way around the X, Y, and Z axes are. We'll just quickly show this. I don't know. Oh, no, doing all right. So depending on the coordinate frame, the attributes took a very long time to generate. The attributes of the sky coord and how you access the individual components have different names. To access the names are printed here in this representation. So you access them with X, Y, Z here, right? And above here, we access the latitude and longitude with .lat and .long. And that's getting you the individual components of like the 3 vector points by coordinate. You can also, as you might have seen earlier, see TX and TY for Helioprojective, which stands for theta X and theta Y, which is just stealing notation from the paper that defined the coordinate frames. As I have already mentioned, you can have frames which are defined at an observer. So this is, you construct this in much the same way as you constructed the heliographic Stoneyhurst frame. You construct this frame object, you give it an obs time, we're using the same time, but then you give it an observer, and the observer is itself another coordinate object. So you're describing the location of the observer at this heliographic coordinate we defined earlier. So we were 10 degrees longitude, 20 degrees latitude, and AU away. By specifying that coordinate frame as the observer argument here, we're saying that's where our spacecraft is. And you can define the location of the spacecraft in any AstroPy or SunPy frame that is supported, and you can pass it through to the observer keyword argument, and it'll use the coordinate transform graph to convert it into heliographic Stoneyhurst for you. So we're constructing a sky coord with this frame, with our point of interest being 123 and 456 arc seconds. And you can see in this representation that Brett talked through earlier, you've got the obs time and the radius of the sun. But now, what Brett described as, and some more metadata, is actually a whole nother coordinate frame that we just created earlier that describes the location of the spacecraft in the solar system. You can have this obs time and our sun be different, but there'd be dragons, don't do that.
So it's worth noting too that coordinate frame attribute on the map that I showed in the last notebook, that all it's doing, it's constructing that attribute by doing exactly this HPC frame line, and then it's constructing the observer based on the keywords that are in the FITS files. There are specific keys in FITS that specify the observer location. It's using those to build this HGS coord, and then it's building a helioprojective frame based on the date in the FITS file and then that observer.
So the question was whether it's possible to obtain the orbital parameters like eccentricity. No, because in the well, in like a map like we loaded earlier, we've just given a single position point, right? And here, this coordinate framework like this has no real concept of orbits. It's all just points in space at a given time. And you can have like multiple points at multiple times, but there's no like orbit propagation stuff built into AstroPy coordinates. There is another package called PolyAstro, which uses AstroPy coordinates to do orbit propagation and like that kind of stuff. So you could use PolyAstro to generate, you could specify the frame and then convert an orbit parameter into one of those frames or something you wanted to do. It's all like, again, there's AstroPy coordinates is one of the things that is like implemented in AstroPy core, but is like used in many different places like PolyAstro and SunPy and stuff all kind of extend that framework and add on different bits to it. Kind of nicely modular. Okay, actually doing vaguely okay for time, I guess. Any other questions before? Okay, so earlier in the Fido search and download session, I mentioned that some of the Fido clients supported like metadata only queries where there aren't files attached to the records, they're just providing you information about things. And one of those is the HEK, which stands for Heliophysics Events Knowledge Base. So what we're going to do in this quick example is search the HEK for flares that happened between our CME start and end time. So we're constructing the time atta like we did earlier, and then we're passing two HEK specific attributes to Fido search. One is the event type FL, which is the HEK secret code for flare. And the other one is HEK.FL.GOES-CLS, which is the GOES observed flare class. So as Will mentioned earlier, briefly in the time series thing, the GOES graph, if that flux goes over certain values, that's a flare classification system. So here we're searching for any flare above C 2.5, which is some certain what irradiance in GOES, is that the right noun? I guess, yeah. So this HEK result is a standard Fido result object, much like we saw earlier when we were searching the VSO. It's the same. What? Two? Oh, right. Okay. I was reading that wrong. Yeah. Earlier when we were searching like VSO and stuff, they tend to only return like a few columns, just enough to describe the data product, and then you download the data product. Here we're searching the HEK, which is metadata only, so it has many, many lots columns full of various different information about that flare or those two flare events detected. We don't really want to have to carry all of that around for the rest of this example because it makes things ugly. So we're gonna this HEK result HEK object that we're accessing by accessing this HEK key of that results object is just an AstroPy table, like Brett was demonstrating earlier. So we can pick out the columns we want by specifying the names of those columns to that, and then this gives us back an AstroPy table object, albeit subclassed for slightly, but we now have the start time of the event, the peak time of the event, time of peak flux, the end of time of the event, the flare class, both of these are M4, and then the HPC X and Y locations of that flare event on the sun. So we can once again access the GOES time series, and oh, no, we can't. Wait for it. Yeah, I know I can. No, wait, that's not right, is it? That /storage lives on my computer at home. It's not going to be here. And then we can do the same thing. Do not like your MacBook. It is weird and alien to me. Sorry, say that again. Yeah, you can do this either absolute or relative, depending on, what you fancy. So we're going to load all this data again. This is obviously like the same loading code we did earlier, so I'm not going to go through it too much. And then we can plot this time series using ts.plot, same as, keep wanting to call you Drew today. I've done too many of these things with Drew, as Will did earlier. And then we can use matplotlib to annotate the time windows that the HEK gave us for these flare events. So you can see we've got 2 highlighted regions for these 2 flares on this time series. Everybody okay up to here? Yeah. Okay, so using that HPC X and HPC Y keys in that HEK event table, we can construct a coordinate object as we just did manually. So we're going to, because we only have HPC X and HPC Y, they're not exactly a fully fledged coordinate information there, but with a little bit of asking your friends, you can find out exactly what they mean by HPC X and HPC Y in HEK. And we know that the observer is defined to be the Earth, and we can use the event start time as the time for that coordinate frame. So as this is a SunPy function. SunPy.coordinates has a get Earth. Is that AstroPy? Okay, I'm going to have to find out now. I think there's one in AstroPy as well. Anyway, there's a get Earth function which returns you a heliographic Stonyhurst coordinate object for the Earth at a given time. So we're going to get the location of the Earth at the event start time, and then we're going to construct a helioprojective coordinate frame, again, with the obs time set to the event start time and the observer being the Earth. And then we're going to use that frame to take the columns, which are like quantity array column objects in the table, and we're going to construct a 2 long sky coord for both those flare locations, except we're not, apparently. What? Oh, we're iterating over the flare table. I guess they are, yeah, okay. The observer time and the obs time are different. So that's why we're constructing it. If you do have lots of coordinate points in the same frame, you can construct a single sky coord with n-dimensional coordinate points, which allows you to do fast vectoring stuff. But if you have different observers, that doesn't work. Different obs times does, but different observers doesn't. Right, and then we can take the maps that we have, the AIA map and the stereo map, and we can plot these locations on both. So it's worth noting that this AX plot coord method in AstroPy here is doing some serious magic at this point. So we have constructed 2 helioprojective coordinate frames and a point in each frame with an observer at the Earth for a given obs time. When you want to plot those locations on these maps, you have a different observer and you're taken at a slightly different obs time. So it is doing a full helioprojective to helioprojective coordinate conversion where it goes from a helioprojective frame centered at Earth to HGS, and then I can't remember the exact path through the transform, but to HGS and then back to a different helioprojective frame. So the observer shift is taken into account, as is the time frame shift, and lots of other things. That coordinate transform only works because it's on disk and it's assumed that it's on the solar surface. If you want to do that transform for off-disk points, there is a helper called assume spherical screen, which assumes your point exists on a, like, what is it by default? 1 AU, or like distance to the sun screen, which lets you make a good approximation for many purposes of doing off-limb observer shift coordinates. Obviously, if you want to like use Gaia to get distances to stars and then do it for actual points off disk, then so much the more accurate. So we've got two flares. One appears to be in the point where our CME is coming from, and the other one appears to be in a slightly different location on disk. Okay, before we get into reproject, is there any questions on all of that? Either you all are way more awake than I think you are, or you've already fallen asleep. Okay, so what we're going to do in this last example before we can all go and get some dinner is we're going to take the 3 images we've been working with this afternoon, that's a lie, this evening, and we're going to put them all on a single helioprojective map. Heliographic map. And heliographic Stony Hurst coordinates. Before we go and do this, we need to do a little bit of standardization between these 3 maps to get them all lined up together. The first one is the eagle-eyed of you may have thought it slightly weird in the map session earlier when Will said this map has a specific radius of the sun. You're like, well, the sun only has 1 radius. But it turns out that is maybe not true. And the way that you calculate the coordinate systems if you're an imager kind of depends on you assuming a value of solar radius. And stereo and SDO have assumed a different value of solar radius, both arguably valid, but annoyingly not the same. So the first thing we're going to do is throw away all the no doubt hard work that the SDO and stereo teams put into figuring out what value of solar radius they wanted to use and just make them all the same constant value from AstroPy. So that's that. If you don't do that, when you convert from you convert into heliographic and it's not the same heliographic frame because you've assumed a different radius of the sun. And then when you try and collapse it all onto one map, it goes a little squiffy, which is a technical term because I'm being recorded. The other thing that Will pointed out earlier is that the EUI and the AIA and stereo maps have different units. Oh wait, no, mistakes were made. Mistake. The EUI is count per second. It's a level 2 file. It's already been normalized for exposure time. And the AAA and stereo ones are not. So the first thing we can do is just divide the maps by the exposure time. So this, for those of you who maybe aren't so familiar with Python, this / equals is an in-place arithmetic operation. It is functionally equivalent to doing it just avoids an intermediate variable and saves a little bit of memory. So now we have the AAA and the stereo maps have a unit of count per second. So they're all in the same units, they're all normalized to their exposure times. Next of this very long run up to a pretty graph is we need to fix the degradation of the 304 channel in AIA. So AIA has been in orbit around the Earth since 2010. I remember this because when it launched, its downlink was faster than my broadband connection. And we want to correct that degradation into that detector so that it's a bit more equivalent to the nice, fresh, shiny EUI detector, which is not been in orbit since 2010. So we're going to use AIA-Py for this. As Will mentioned earlier, is AIA. AIA is a SunPy affiliated package built by the AIA instrument team, and it provides AIA specific functionality, such as modeling the degradation curves and providing tools to compensate for them. So we're going to construct an AstroPy time object and make it into time range. And then we're going to plot the degradation curve for the 171 and 304 channels of AIA. This is apparently doing some math. I have no idea what this function does, but if you want to know, ask Will, he wrote it. So you can see that at the beginning of their lifetime, they had a scaling factor of 1. And now down here in 2022, we have we're getting a tenth or less of the counts per photon or whatever. I don't know, detectors, observations, it's all beyond me. So we can now use the correct degradation function again from AIAPy to make a new version of our AIA map with this scaling factor applied. It's just a scaling factor, right? So it's going to increase the values of our counts per second. Right, and here we are at Reproject, some 10 minutes later. So before we actually do our reprojection, we need to tell Reproject what the coordinate system we want out is. So reprojection in AstroPy Reproject is you take an image in one coordinate frame and you use it to make an image in a different projection. So you can do, if you go into the SunPy example gallery, there's quite a few examples of this, but you can do it to say, you take a AIA image and reproject it to see what it would look like if EUI had taken it. Or you can do what we're going to do here, which is take one or more images and reproject them so that your pixels are latitude and longitude in heliographic coordinates instead of helioprojective coordinates. SunPy provides a helper function called makeFitsWCS real catchy name, which makes a header out of these high-level coordinate objects like SkyCoord and AstroPy time, and uses that to generate a fits standard WCS header. So this, I'll go through the arguments to this function one at a time and kind of explain them as I go. So the first one is the shape of the output. So this is our desired array size for our output image. As that comment helpfully points out, we're going to keep this nice and small so that we don't OOM all your kernels, but we might do that anyway. If you have more memory, you can up this and get more resolution in your resampled image. Obviously, there is some point where you're oversampling, but we won't worry about that too much. The next point is the observer location. No, it's not, sorry. It's the reference frame. So it's the reference frame and the reference coordinate. Now, we didn't go into details of how WCS transforms work today because I thought that it would bore at least half of you. So I'm just going to skip over this and say this is the 0th point. This is the coordinate for a specific pixel in the image. I think by default, this function is making it the world coordinate for the center pixel of the image. So we're saying that it's 0 degrees latitude and 0 degrees longitude at the center pixel of the image, and they're in degrees and they're in heliographic Stonyhurst coordinates and they're at a specific time. So we're giving lots of metadata in this one line. We're saying what the reference coordinate is. We're implicitly saying what the reference pixel is, and we're saying it's in HGS and everything else. The next argument is scale. So that's how many degrees of heliographic latitude and longitude we go up per pixel, we go away from the reference point. We're specifying the wavelength, which is just doesn't actually need to be specified for the transform, but is good to keep around. And finally is the projection code, which is CAR, which is the fit standard projection for plate Curie projection. If you want to know any more than that, read the paper or find me in the pub later. So we now have a AstroPy WCS object. So we've made the header and then we've made an AstroPy WCS object. This is the same object that Brett and Will spoke about in different contexts earlier. And then we're going to call this reproject and coadd function that lives in reproject. and we're going to pass it in a list of, oh, thank you very much. Oh, too kind. I'm going to pass it in a list of our 3 maps, our degradation corrected AIA image, the stereo map, and the EUI map. We're going to pass it the output WCS, we're going to pass it the shape we want, and we're going to tell it what reproject function to use. Reproject interp is the fastest and least accurate reprojection function implemented in reproject. There are 3 plus Heliophysics. Reproject interp uses SunPy map coordinates and will grossly undersample your input arrays if you don't invoke it perfectly with the right resolutions. There's one which is called Reproject Adaptive, which is a bit smarter and especially useful for doing stuff at the edge of the solar limb, but anything with any significant scale changes, it's pretty good for. And the last one is Reproject Exact, which uses spherical polygon intersection on the sky plane to do significantly more accurate reprojection. They take progressively more and more CPU and memory. So once again, to not kill HelioCloud, we're using the simple one, which is perfectly fine for making visualizations. But if you wanted to do science on the fluxes, you would probably want to use something else. So reproject and coadd has returned an array and a footprint. We're going to ignore the footprint for now because it is basically meaningless for reproject interp. And the array is our new HGS map. We're going to construct a map from the new array and the header we made with our helper function earlier. And then we're going to plot it. And there it is. And yes, I did promise you a pretty picture. We're getting there. So you can kind of see here that you've got 1 image, 2 images, and 3 images all stacked together. This is in heliographic longitude and latitude. So this is the 0th meridian of heliographic longitude. So that's like where the Earth is looking at the sun. And then you've got latitude and longitude away from those reference points. So as you can see, these 3 are all overlapping, and we've stuck them together with minimal attention to the differences in their background scales or their relative scientific usefulness. So the pixels at the center of the disk in heliographic coordinates are smaller. Yes, that's right. I'm still awake. And so we want to weight those higher because they have higher resolution than the pixels that are at the edge of the sun in helioprojective coordinates once you've done the reprojection. So we're going to create a weighting function which like tells reproject to, is this the thing that, this is the one, don't run that cell. There we go. But I need to do, it's dead Dave. Everybody's dead Dave. In the run menu, there's a run everything above a selected cell, which you may find useful. So if you're following along at home, you are going to want to write this little bit of witchcraft. So for each map, we're just going to make it a little bit smaller so that we don't eat all of the memory, all memory everywhere. There we go. Does that require pixels? Does that require one argument or 2 arguments? One argument, units. Will knows. By the way, this question mark thing is a IPython Jupyter thing that prints the docstring of a function. It's very useful. If you're not in Jupyter, you can use the built-in help function to do a decent equivalent of the same thing. Little tips. With units, so we're going to times that by pixels. And I'm going to say 4M in maps. For those of you who maybe aren't familiar with this, this is called a list comprehension in Python. Look it up when I don't have under a minute left. Right, and now we're going to run this. So the reason that this ate all the memory is because it created 3 4K by 4K arrays. No, it didn't. It created 1 4K by 4K array and 1 whatever the size of EUI is and 1 2046 by 2046 array. Anyway, it created lots of arrays. So this map all coordinates from map is a helper function in SunPy, which gives you a sky coord, 1 coordinate for every pixel. I won't go into too much into the rest of that. And then we're going to create some weights. We're going to fiddle these weights a little bit so that they work. What we've done is we've used the Z value of the coordinate, so the distance from the observer to the point on the surface of the sun, to weight things that are closer to the observer higher than things that are further away. So we're using that to weight things at the limb less. And then we're going to call reproject and coadd one more time. I'm nearly done the promise with these weights that we just calculated. And we're also going to pass match background and background reference, which just help tell reproject to do some clever balancing of the relative intensities in things. And then we end up with this. The only other things we've done here is we've plotted the flare location, which has converted from helioprojective to heliographic coordinates. And we've also plotted the limb, the solar limb as seen by the 3 observers. So the green observer here is the EUI limb, so that's the edge of the sun seen by EUI. This is the edge of the sun seen by AIA, and that's the edge of the sun seen by EUI. I keep getting EUI and EUVI confused, but I feel like you can understand why. You might notice that they're offset a little bit, and that's because the observers are at different relative locations to the equator of the sun. And with that, I'm done. Any questions before the bus driver kills us? Cool, correct answer.
Feel free to leave all of the cards I gave you all at the beginning of the day on the table, so that they're there for tomorrow. And also expect the bus to come at 12:30 tomorrow, not 11:30. And the location for where the bus will be is updated on the website now. So you should be good.
Oh, there is just one more thing I forgot to mention, which is I've left a pile of SunPy stickers on the front desk down here if anybody wants to come and get one on their way out.